Hey guys, and welcome to this Kotlin crash course in which I will really go over all those main language features of the Kotlin programming language. So it really does not matter if you have no programming experience at all and you now want to dive into it with Kotlin, or you maybe already have programming experience in a different programming language and now found Kotlin interesting for some reason and want to dive into it. In this video, I really want to strike a balance between time investment on the one hand, to not make this a 10-hour video that you maybe have to watch over multiple weeks, but also giving you enough depth so that you can really dive into your own Kotlin-related projects after watching this video, because you have enough knowledge for that. So this course will cover, I would say, 80 to 90% of the language features that Kotlin offers. The rest that I won't cover here is either not very often needed or very advanced, which you will stumble over on your way anyways later on. And I also do have a dedicated Kotlin playlist, which is a bit older, I think 5 years or so, when I record this video, which you're also still welcome to watch. This Kotlin playlist in full is of course longer than this video. So if you say you're just short on time or you want to watch a more modern video, then please stick to this one here. And in case you don't know me and you're maybe new here on this channel, I'm Philipp. I'm writing code since I'm 13 years old. And nowadays I mainly focus on native Android development with Kotlin, but I also use Kotlin for other fields like backend development or Kotlin multi-platform. So the vast majority of videos on my channel is completely Kotlin related. So if that's interesting to you, then definitely make sure to subscribe. And I actually don't want to talk a lot more because I really want to get into coding right away. Just a few last words of why Kotlin is actually a cool language and why I like it so much. On the one hand, we have the interoperability with Java. So if you're new to the programming world, Java is a very, very popular programming language that is used across the industry, especially for very big enterprise projects. So a lot of software out there is based on Java, which also has the advantage that Java programs run on any platform. And Kotlin is actually interoperable with Java. So that means it actually translates down to the same type of machine instructions. We call that bytecode that Java does as well. So under the hood, when a Java or Kotlin program is run, our machine does not even know whether that was written in Kotlin or Java on our higher level. And that's very cool because we can really mix Java and Kotlin code in a single project and maybe make use of older Java code other people have already written for us and use that in our Kotlin-based projects. Then other than that, Kotlin is just a very nice language. So there's a lot of syntactical sugar, we say. That's in the end just a fancy term for kind of shortcuts in code to achieve certain things in a very easy way with writing very little code. And lastly, why I like Kotlin so much is that it's just a super versatile language. So we can do a lot with it. We can write native Android apps with it. That's what I specialized on. So Kotlin is the main language for native Android development. Then with Kotlin, we have Kotlin multi-platform. So that's also a technology that comes from JetBrains, the makers of Kotlin, which allows us to build Kotlin software for multiple platforms. So for desktop, for iOS, for Android, for web, and all that in a single code base. And we can also use Kotlin for backend. So Kotlin has its own server-based framework, which is called Ktor. At this point, when I record this video, Ktor is not too popular in the industry yet. It's a great framework. I've used it before. But you can also use Kotlin for Spring Boot. So Spring Boot is the most popular Java-based backend framework to just write server architectures, server code. And since I said Java and Kotlin are fully interoperable, that means we can also write a Spring Boot backend, which was originally meant to work with Java. We can also write the entire code for that in Kotlin. And Spring Boot is way, way more established in the industry right now. And it's a much more mature backend framework. So if you want to dive into backend development and you like Kotlin as a language, then I really recommend to take a look at Spring Boot and Kotlin in combination. Okay, but I've talked enough. Let's dive into actual coding and see what cool things we can do with Kotlin. And for that, the first thing you need to make sure is that you've installed IntelliJ. You can see this is the website from JetBrains. As I mentioned, JetBrains is also the company that made Kotlin as a language. And they also make all those cool IDEs, so integrated development environments. That's in the end the software in which we type our code that just offers lots of useful tools in order to debug our code, to spot issues, in order to just run our code with a single click. So in the end, we could just type our Kotlin code in a simple text editor. That would work, but everything that comes after that in order to be able to run this code, that is what we would need to do manually. So we would need to manually compile it down to instructions the computer understands so that we have a real executable file. And in such an IDE here, all that work is taken from us, so we can really focus on the code. You can see there is a syntax highlighting here, which just makes code much more readable overall. So in case you don't have IntelliJ yet, make sure to download this here. I will put the link down in this video's description. This is the ultimate version, which is paid, but there is also a community version of IntelliJ here, this one. So make sure to download this one if you want the free version, which is completely enough in order to follow through this video and write your first Kotlin code. And when you've then installed IntelliJ in your machine, you've launched that, then there must be some sort of button to create a new project. It will obviously look differently for you than for me if you freshly installed this, which is why I can't show you the exact look as it's likely for you. But the moment you open IntelliJ, there must be a button to create a new project. You click this, and then your window should look somehow like this one. As I said, I have the ultimate version, so I have maybe a few more options than you do, but you should definitely have this Kotlin option here under new project, so you can really pick what kind of project we want to create. So we have a Java project, Kotlin project. Here, Ktor, for example, is the Kotlin backend framework I've mentioned. This, I think, is only included in IntelliJ, in the ultimate version, I mean. We have Spring Boot, so that is the Java-based backend. And here we get some sort of error, it doesn't matter. But you can see you have some kind of project templates here directly. We want to create a Kotlin template, and we can choose a project name. So for this one, that would be Kotlin Crash Course, for example. The idea project folder is the default one where these project files, so all the code we write, will be stored. For the build system, we can really leave this at Gradle. So the build system is in the end responsible for taking all of our human readable source code and packaging that into an executable file that we can then also run directly here in our IDE. The JDK is the Java development kit, so that includes all the Java code functionality that we may want to use in code. As I said, Kotlin relies on Java and the JDK. That is why we can choose the specific version of the JDK here. IntelliJ already ships with its own integrated JDK, so you should see something here. Maybe not 21, but you can just pick the JDK of your choice. For this video, it really shouldn't matter whether you pick 21 or a lower version. For Gradle DSL, we can leave this at Kotlin as well. That's also more advanced. We don't want to add any sample code, and we can just click Create here in the bottom right corner. So here we are. This is how it should look like for you after creating this project. This is the first file that opens, this build.gradle KTS. As I mentioned, these Gradle related things I don't want to get into here. Just maybe what's worth noticing is that here in this file, in case at some point you want to change your Kotlin version, so the programming language also has its own version, then we can do this here by just changing this version string to something you find maybe on the Kotlin website. So JetBrains obviously also consistently pushes new updates to this to Kotlin as a programming language. So we have new language features, new things we can write in our code, maybe fixing some bugs, making certain things easier. So if you need to change the Kotlin version at some point, this is the place to do it. But as I said, we want to just close this here. We don't want to care about this file. And first of all, take a little look at the project structure that was created here. So just the folder structure. So a lot of files actually have been created and a lot of folders. We want to ignore most of these and really focus on what's in this SRC folder. That stands for source and includes our source code. Specifically here inside of this main, so that contains our main code that really includes the code for the actual program we are developing. And then we have this Kotlin folder in which we can now place our real Kotlin files where we type our Kotlin code. There is also a resources folder, which could be used if you maybe want to include some images or external files in your code. We don't need this here. We just want to go to this Kotlin folder, right click here and create a new Kotlin class or file. If we do this, then we get this type of dialog where we can simply enter the name of the file we now want to create. And typically every program needs some sort of entry point. So the moment we click run, we execute our executable, then the program of course needs to know at which point in the code it actually should start executing. And in Kotlin, this point in the code that initially executes when we run the program is called the main function. So let's call this file main and we select file here and then simply hit enter. And then we have our very first Kotlin file, which has the KT abbreviation. And here we can really do what all programming tutorials start with, and that is writing a little hello world program. So just a program that prints out hello world to the console. So most programs you maybe work with on a daily basis have some kind of graphical user interface like this IDE here, this program that we see something. That's not what we'll do here. That's a lot more complex. But the most simple form of program is just a program that is able to receive inputs in some way and give us outputs in a different way. And that just works via the console. So we can give text inputs and we get text outputs. So what we can do is we can write function with fun main and then open a block of code here with these curly braces. If you're new to the programming world, then we really don't want to overthink what this means yet. We will get to what this actually means later in this course. But in the end, we just define this part of the code as our entry point now when we run our program. And then very commonly in programming language, not only in Kotlin, we have these curly braces to just indicate what now belongs to this specific main function that gets executed when we run our program. And what we can now do here is we can call println. And you can see there's also AI auto-completion here enabled. Maybe that's not enabled by default for you, but you can enable this in the settings. But println is in the end just something that we can use in order to pass some kind of text here that gets printed to the console. So it's not going to get printed by your actual printer on paper, but in the console. So if we use this and we then type quotes, hello world, exclamation mark, and we then click on this little green play arrow and run this main KT file, then all this will be packaged together. We wait a little moment, and then here our console will open up and we do see hello world. So this is really now the place that will give us the outputs that our program will generate. And println is really just the way to take a specific result in our code and put that out to the console so we can really see what that result is that we somehow have internally in our code. And with that, we can come to the next concept, which are so-called variables. You maybe know variables from math back then in school, where you had some kind of X and Y variables that in the end just hold a number. And that's exactly what we can also do in our code. So we can define numbers by saying val, I think that stands for value, and we could define a number X, for example, 5. So we say it's val, we call that that value X, that variable X, and we set it equal to 5. So this is important to understand that this equal here in Kotlin is an assignment operator. That is how we call it, because we want to assign a value, this number, to this variable X. And then instead of printing hello world, what we could also do is we could now take our variable and print that. So now without quotation marks, because it's a variable and not a raw string or a raw text that we want to print as it is. But here we actually don't want to print X, but the value behind X. That is why we don't use these quotation marks here. If we now rerun this, then you can see we get the output 5, because that's the value of this X. And every such variable in Kotlin also has a specific type. Because of course in math there are different types of numbers. We have whole numbers, we have decimal numbers, and we may also have other data types that could be useful in our code. And what you actually don't see here is that whole numbers in Kotlin are so-called integers. So what we could also do is we could explicitly define this X variable here as an integer by using a colon here and saying int. Right, simply writing int. You can see that's grayed out. Whenever IntelliJ grays something out, that means it's redundant. You don't need to specify this, but it's also not a problem if you leave this. So running this code here will really just be the exact same result as before. So this just means, hey, we have a variable X of type integer, so it must be a whole number, and the value of that is 5. So why can we actually leave this type here away and just leave it at X is equal to 5? And the reason is called type inference. Sounds very complex, but that's in the end just a mechanism that takes a look at the actual value we assign to a variable. And based on the value, it can already determine what kind of type that specific value has. And here, this value 5 is obviously a whole number. So the Kotlin compiler, what translates our actual Kotlin code down to instructions the computer understands, that will see, okay, that's actually a whole number. So we could say this X variable has the type integer. If we now want to use a decimal number, then we have two data types for that. On the one hand, we have so-called float numbers, and on the other hand, double numbers. So if we want to say this 5 should be a float number, and I will get to the difference to double in a moment, we could specify this float here. And then suddenly we get a complaint here by our IDE, this 5 is now underlined. And if we hover over this, it says the integer literal does not conform to the expected type float. So we say our variable should be of type float, but we then assign a whole number, and that doesn't match for the IDE. Instead, if we want to declare such a floating point number that supports decimal places, we need to append an F for float. And then again, our float will turn gray because it's redundant. And if we now print this again, run the program, you can see this time it actually prints 5.0. So this is also how we could now specify decimal places. just with a dot, and then 1, 2, 3, for example, we print this, and then we get the decimal number. And the same thing actually works with so-called double numbers. These we can declare by just leaving the F, but making sure there are some sort of decimal places. So if we print this, this is now exactly the same output. So what's the difference between double, which we could also specify here, double, like this, and float? Well, the difference is just the size in memory. So float numbers in Kotlin are 32-bit numbers, so we have 32 bits available, either ones and zeros, in order to model a specific number. Double numbers are 64-bit, so they are twice as long, and if we have more bits available, then that also means we can model more accurate numbers. So if you don't care too much about accuracy, I would recommend to use float, because these numbers require less memory or less RAM. If you need a lot of accuracy, then make sure to use double numbers instead. One more interesting data type are so-called booleans. Because with booleans, we can simply say a value is either true or false. These are the only two options we can assign to a boolean. So instead of setting this to a double number here, we could also say we set this to true, and then x would be a boolean. And if we now run this, then we would obviously just get the true printed to the console. So these booleans will later on, of course, be important to just execute certain code conditionally, for example, to say, hey, I only want to execute this code if a certain condition is true, or if a certain condition is false. That will also work. And the last data type that I want to cover, at least at this section in the course, at this beginning here, are so-called strings. And we've actually already worked with strings before. Strings are in the end just text, so just some kind of sequence of characters. This could be a full paragraph, this could be a single word, this could be a sequence of numbers that we don't interpret as an actual number, but just a sequence of number characters. And strings we can declare just like we did before with quotes. So we could say we have x, we set this to hello world, and if we then print x, then we see the hello world string again, just that the string is now saved in a variable. And these 5 data types are what we call the primitive data type. There's actually one more that we'll cover later here, but you can really think of these as the most fundamental data types in Kotlin. So integers, floats, doubles, booleans, and strings. However, what if I tell you that val is actually not the only way to declare such a variable? There is also var, which stands for variable, I guess. And if something is variable, then that means it could change. And that's exactly what we get with var. So if we want to assign a certain value to a variable, and we want to be flexible, we want to be able to change this value later on in our code to something else, then we can only do this if this is actually a var and not a val. So here we could say we declare this x and set it to hello world, but then in between we say, okay, now x is equal to something else. We could set this to bye bye world. And if we then print this, we actually get the latest value that x has at the point of time where we call this printline function. You can see it prints bye bye world. And here again, you can see this is grayed out because it's redundant. The IDE is like, dude, why do you set this to hello world if you just set it to something else afterwards? You don't need to set it to hello world in that case. So you can see the program here is really smart in telling us how to improve our code, but technically this is fully correct code. Okay, I think we can make a check to variables. I think that should be clear. Let's get next to so-called arithmetic operators. And that's something all of you know. We are, of course, able to add numbers in our program, in our Kotlin code. We are able to subtract numbers, divide, multiply, and all those operators that have something to do with calculations are so-called arithmetic operators. So we could say we have a val x, that is equal to 5, and we have a val y, that is equal to 9 maybe. And then instead of just printing x and y, we could say x plus y. And if we run this, I think you get this, it will print 14. The same way we can subtract numbers here with a minus operator that prints -4. We can divide numbers. That's now interesting because if we divide whole numbers, we have 2 integers, and we divide 5 by 9, well, then that's definitely not 0, but if we only allow integers, then a division of an integer by an integer also must result in a whole number again. That's at least the rules that Kotlin defines, and lots of other programming languages as well. So for integer divisions, where we divide integer by integer, the result will always be rounded down. So if we actually make x a 9 here, then you will see this was a perfectly valid division, and then we do get a valid result, so then it prints 1. And if we make x a 10, for example, then we also will get a 1, because 10 divided by 9 is a little bit above 1, and therefore it will simply cut all the decimals, and then the 1 remains. Multiplications, of course, don't have that issue with whole numbers, so we can multiply with this asterisk operator. We run this, and then we get 90 as the result. Another interesting arithmetic operator that we maybe don't know directly from math is called modulo. So modulo is what we use with the percentage sign. If we run that, then it will give us 1. So the same result that we also got with the integer division, but the interesting part now comes if we bump x to something like 11 and we rerun this, then it actually prints 2. So what modulo will do is it will actually divide x by y, and the result of this calculation is then the remainder. So the 9 fits exactly once in our 11, and the remainder is 2. So that is the output of modulo. And these are already all the arithmetic operators that we have in Kotlin. There are some more variations of what I showed you before, especially if we make one of these variables here a var, then there is a shortcut operator that we can use, which is x++, for example. If we actually say x plus y here again, and we call this, then it will print 21, even though 11 plus 9 is actually 20. So what x++ will do is it will actually increase the value of x by 1. So x++ is just a shortcut for x is equal to x plus 1. So we just bump x by 1, take the new result of that, and write it to our x variable again. Same as that, we also have x minus minus, that will obviously decrease the value of x by 1. But if you want to do that, it's of course important that x is really a var or not a val, because if we make this a val, we will get an issue that says val cannot be reassigned, because what happens here is, as I said, we calculate x minus 1 and then reassign the result to the variable x, which doesn't work if we make it a val, but only var. And what we have in Kotlin is if we want to do something like x is equal to x plus 5, so we want to bump x not just by 1, but by 5 and rewrite the result to the variable of x, then for these types of operations, we also have a shortcut, and that is x plus equals 5. So this line is now the same as this line. So we can remove this, and if we now run this, this gives us 25 because 11 plus 5 plus 9 is equal to 25. And if you do it like this equals is actually important, because if you don't have this, then it will technically also work. This won't cause an issue or so, but if we now run this, this just gives us 20. Because if we just write x plus 5, well, then it will increase the value of x by 5, but it won't do anything with the result. It won't reassign that to x. So the calculation will be made, but the result won't be saved in the x variable again. So this would print 20 instead of 25. But just like I showed you before with plus equals, we also have minus equals, we have divide equals, and multiply equals, which actually do exactly the same as plus equals, just with the other corresponding arithmetic operators. However, arithmetic operators are not the only type of operators we have in Kotlin. The next type of operators I want to cover are so-called comparison operators. So if we want to compare two values, and there are multiple ways how we could compare two values. And with two values, I really don't necessarily mean two integer numbers. This could, of course, compare any two values. This could also compare two strings, for example. So if we make this a val again, and we maybe now have these two numbers in our code, and we want to compare if these are the same. So is the value of x actually the same as the value of y? The way we can do this is we can say equals equals. So single equals is the assignment equals, where we want to assign a certain value to a variable. And double equals in Kotlin is a comparison operator. So we want to compare whether this value is actually the same as this one. And well, what needs to be the case now with all these comparison operators is that the outcome of that now isn't a number anymore, like there was with the arithmetic operators when adding two integers, for example, but the result of such a comparison can either be true or false. So x and y can either be the same or not, but there are no other options. And that's exactly what we then also get, a Boolean. So this is false because 11 is not the same as 9. And the same way we have other comparison operators. For example, if x is actually larger than y, if we run that, it will give us true because 11 is larger than 9. If y would now also be 11, then that's false because 11 is not larger than 11. If we want to check if x is larger than or equals to y, then we can use larger than or equals to y. And then this will again give us a true, so then the other number is actually including in the check. Same thing for less than and just less. So all these comparison operators just give us a true or a false value, which we can then do something with in our code. And this true or false value is of course a Boolean, which we could technically again save in a variable. So what we could do is, we could say, well, are numbers the same? And then we say x is equal to y. So this is a perfectly valid expression, and then we can say, are numbers the same? We run this, and it will give us true, because 11 is the same as 11. So it will first evaluate whether x is actually the same as y, which is true. Then it will take this true value, save it in this Boolean variable. We can also see this if we actually hover over this here, and then wait a moment, we can see that this is actually a Boolean. So that is the inferred type. And if we then want to print this Boolean, well, then it will obviously just print true. And we can, of course, also combine these comparison operators with arithmetic operators. So what we could do is, we could get rid of that and say, print x modulo 2 and check if that's actually 0. So what would that do? It looks quite complex if you've never seen this before, but in the end, we divide x by the value 2. This results in the remainder of that division, and we check if the remainder is actually equal to 0, because what does that mean? If the remainder would be 0 after division by 2, then the number would be an even number, and if the remainder would be 1, it would be an odd number. And there can't be any other remainder other than 0 and 1 if we divide by 2. So if we run this, then you will see false, because 11 is not an even number. And we could also actually take this expression and put that in a bit more readable string. So we could say, is x an even number? And then in order to now take this value of x and include it in our string, so just doing this would not work. You can see this would simply print x as a character, but we want to print the value of x. So what we want to do is we use this $sign. That is a string template operator, so that instead of using x as a character, we include the actual underlying value of x. And if we have a bit more complex expression here, like we had before with the modulo operator, comparing that to 0, then we can also use curly braces here. And in here we can really put any type of expression that we want, like what I cut out before. So whether x divided by 2 or x modulo 2 is actually 0. So if we now run this, it says, is x an even number? No, in this case not. If we change x to 12, rerun this, then it says, okay, x is actually an even number. And the last type of core operator that Kotlin has, there are more, but the last type of really fundamental one are the so-called logical operators, specifically the and the or operator, because both of these operators can be used to chain multiple Boolean conditions. So let's say we want to print whether x and y are actually even numbers. Then we could say, are both even, and we set this equal to x modulo 2 is equal to 0. This would now check for x. But we now also want to check whether y is actually divisible by 2. So we somehow need to replace this check, just with x being replaced with y, together in a single condition, so that we get a single Boolean value, whether both are true or one of these at least is not true. And that works with the double AND operator. So we can say AND y modulo 2 is equal to 0. And then we can print the value of are both even here in our print line statement. And if we then run this, well, it will give us false, because only x is even in this case. If we say y is now also an even number, and we rerun this, now it gives us true. So with the AND operator, the end result, so the value of this are both even, this will only be true if all single conditions here, part of this AND statement, are true. And if one condition is just false, then the entire thing will be false. That is how the AND operator works. If we now want to check whether at least one of these conditions is true, so we don't care whether that's x or y, but we want one of them to be true, then we can use the OR operator. And the OR operator works via these pipes, so double pipe. If we run this, we get true. So that's an interesting thing. This OR operator is not an either or. So it's not about either x being an even number or y being an even number. The way the normal OR works in programming and in logic theory is that just one of these conditions needs to be true in order to make the full result true. If both are true, then the OR operator will still make the end result true. And this is actually a much more commonly needed operator than if you need an either or condition. That would be called an XOR. But in the development world, it's super common that you actually also want to return true for an OR condition if both conditions would be true. So this way, if we have the condition like that, now it obviously prints true because both are actually even numbers if we change both to 11, then this will now print false, because none of these conditions are actually true, and therefore the OR logical operator will assign a false to this variable. But if one of these is actually even, then it will again give us true, because one condition is enough to make the end result true. But we cannot only chain two of these Boolean conditions here via such a logical operator, but as many as we want. So what's perfectly valid is that we also use an AND afterwards here, and we say something like x plus y is actually the same as 25. If we run this, well, then it will give us true, because this condition is also true. What now happens if we change x to 12? Now 12 plus 14 is not 25 anymore. If you run this, okay, it still gives us true. Why is that? Well, in order to understand this, we need a bit of a deeper understanding of how these logical operators work. Because just like with arithmetics, where certain operations are prioritized, so if we have something like val z, and we set this to 3 plus 3 times 3, then certain operations, specifically multiplications and divisions, are prioritized before additions. So what this won't do is, it won't take 3, add 3 to get 6, and then multiply it with 3 to get to 18. But instead it will prioritize 3 times 3, so we get 9 plus 3 would be 12. That would be the result of z. And the same types of priorities we also have with these logical operators. So AND is actually always prioritized. So what we don't see here, but what the compiler will add is actually parentheses. So it will first evaluate the conditions that are chained via an AND, and then take the end result of that and compare it via an OR with the first condition. And since the first condition, x being equal to 12, is true, since that's an even number, the compiler won't even look at the second condition anymore, because the first condition is already true, and one true is already enough in order to make the end result true. So if we know this is true, then there is no value in actually also evaluating that second condition, since it won't change the end result anymore if this is chained via an OR. So since x is still an even number, this will print true in this case, even if this condition here is not true, since true or false is still true after all. And what you could of course also see is we get a big warning here, because this result is always true, since our IDE says, again, dude, you know the values, so why do you actually have some kind of dynamic condition here that checks if these are even? You can just look at the values, bro, and you know what the end result is, so you could completely remove this, because we know the values of this. However, in a normal program, these values or such variables are of course rarely hard-coded, so that's how we call it if we really give them a fixed constant value during compile time, so when we actually write our program. In real programs, it's much more common that such values are actually dynamic, and we don't yet know these during development. So what actually if we want the user to input a certain number, and then we want to check whether that input is actually an even number? Because that way, we don't yet know whether the number the user will input when the program runs is actually even or odd. And that works in Kotlin via readLn. So we want to read a line in the console, and this returns a string. So this is the data type this function will return. We will get to functions and return types later on in this course. But for now, we can really just use this function and say val input is equal to whatever the user has entered. We can also give some instructions like println, please enter a number. Then we wait for the user to input a number. And then we could say something like, you've entered input. If we run this, then it says, please enter a number. And now it will wait for us to really enter something here. And once we did, it will assign the value of what we entered to this input variable. If we now enter a number, like 50, for example, and hit enter, then it will say, you've entered 50. So that's not fully dynamic. However, you will notice that if we now want to check whether that entered number is actually even or odd, we could of course say, is even input modulo 2 is equal to 0, but you can see we get an error. Why is that if we hover over it? Well, okay, that's maybe not too easy to understand if you're new to Kotlin or programming, but in the end, what this means is it couldn't find a corresponding internal function that calculates this modulo expression for this type of input. Because input, if we take a look here, is a string. And a string could be anything. A string could be hello world text. So how do you take a modulo from hello world text? That doesn't work. There is no real logic behind that. So what we need is we need to tell our program, hey, please take this input and interpret it as a number. So we have it as an integer type. So we could say dot toInt, or we could also say val input as integer. That's maybe a bit more readable. And we say input dot toInteger. So we say toInt. And then we can take this input as integer, which is now of type integer, so it's a whole number. And we use that for the calculation. And we then take isEven and say, is the number even? And we add our Boolean. Let's run this again. Please enter a number. We enter 45, hit enter, and it says, is the number even? No, it's not. If we run this again and we enter an even number, then it will tell us, yeah, that's even. However, what actually happens if we rerun this once more and we don't enter a number? We enter something like hello world. As I said, we just read in a string. This input here is just of type string, and a string could be anything. It could be any sequence of characters. So hello world would be a perfectly valid input here. If we hit enter, then we at least get a very big red text here. And it says exception in thread main, whatever that means, number format exception for input string hello world. So you can maybe kind of guess what that means. It failed to actually format the number because hello world is not a number. So what we say is we have our string input and we interpret that as an integer, but that obviously only works if it is an integer. And if it's not an integer, something needs to happen there. Like we need to tell our code, okay, this is what you should do if the user enters an invalid value. And if we don't specify that, then there needs to be some kind of default behavior. And well, that is crashing the program, because if we don't define this behavior, then the program has no idea how to proceed. Because it's like, okay, what kind of value should I assign to this input as integer if this is actually not a valid number? That's something we need to define or tolerate our program to crash. And that's how we get to another very core concept of Kotlin, which is called nullability. So if we speak of a null value in Kotlin, then that pretty much just means the value does not exist. And we can make use of that by not using toInt, but saying toInt or null. And the return type of that, if we take a look at input as integer, is now int question mark. So every single type in Kotlin, like int, string, float, double, and so on, can also have a corresponding type with a question mark afterwards. The question mark says, this may be an integer, but it may also not exist. It may be null. And if our integer is null, that does not mean it's 0 or it's some kind of random number. No, it really means the number does not exist. So there's definitely a difference between a number being equal to 0 and equal to null. And if we do this, if we now use toInt or null, then what will happen here is if we actually enter an invalid input, let's comment out this isEven. That's how we can just make code a comment. You can also just let's just remove this because you probably don't have the shortcut yet. We remove this line and we just reprint the input. So your input is input as integer. If we run this, we enter a valid number, 45, then it will again give us 45. But if we rerun this and we enter our hello world text again, then it will say your input is null. So that is now what we get by using toInt or null, because it can now return null. It can return an invalid value, a not existent value, if it actually fails to parse that string into an integer value. And that's exactly what happens here if we enter a real string that's not directly translatable to a number. But what if we now want to use this in order to check whether this number is even or odd? Well, then let's type this again. Val isEven is equal to input as integer modulo 2 is equal to 0. But we get an error. It says operator call corresponds to dot qualified call input as integer, blah, blah, blah. Very complex. What does that mean? Well, it now sees this input as integer can actually not exist. And then it also has to consider the case that this value is actually equal to null. And what would that happen? What if input as integer is a non-existent value? How would it take a non-existent value and calculate modulo 2? What is the result? Well, there is no result. So it's unable to actually calculate that. So what are our options there? Well, the most simple fix is at least using the double exclamation mark operator. You can see if we add a double exclamation mark afterwards, then we don't have any more errors. And if we then say even or odd, or let's actually say isEven, is even, like this, isEven, we print this, we enter a number, 45, isEven is false, we enter a hello world text, We again get this red print statement here. This time not with a number format exception, because our code does not crash at this line anymore, since we made sure to properly return a non-existent value if it can parse this into a whole number. But we get a null pointer exception. What's that? Well, what this double exclamation marks operator will do is, it can be used on values that could be null, that could be non-existent, but if they are non-existent, it will simply crash our program. So we didn't really win anything with that. And that's also why it's very discouraged to use this operator, but it does solve the problem here. So what could be a better way that does not crash our program in case input as integer is not valid? What if we maybe just want to assign a default value in the case that the input is not valid? So we say, okay, if the user enters some kind of invalid value, enters hello world, we can parse that into a whole number, then we just want to assign 0 to this integer. So we always have a fixed default value in case this fails. In order to do that, we have another operator which you can use, which is the question mark : operator. And here we can assign a default value. So what this will do is, it will assign the input converted to an integer, but if the result of this conversion is actually equal to null, then this operator will instead take what comes on the right side. So if we run this and we enter hello world, it will now say is even is true, because it will take the default value of 0, take that as the input as integer because it failed previously, and 0 is obviously an even number, so it will say even is true. If we enter a valid number, then everything will still work as expected, then it will say it's not even. But one more operator that also corresponds to nullability in Kotlin is the question mark dot operator. So instead of doing this, we could also say question mark dot, and we maybe call inc, which increments the value by 1. And let's get rid of this is even for now. We would say the incremented number is input as integer. We run this. If we enter 5, it will give us 6. If we enter hello, it will give us null. What does that mean? Well, if we actually need to do something directly with a value that could be null, we can safely call such other functions like incrementing this. This is the same as the ++ operator, by the way. Just that with a question mark dot, we can make sure that this code only gets executed if what comes before is actually not null. If it is null, then the whole result will be null. And that is why we saw the incremented number is null in the case that we entered a hello world text. And the same thing actually works for the rem function, which is the shortcut for remainder. So that does the same as modulo. Just with modulo, we have the operator. With the increment, we also have the operator. But if we want to use this question mark dot operator, what comes afterwards actually has to be such a function. So here we could also say modulo 2, and again say is even is equal to, actually no, we don't need this is even. We could just check whether that's equal to 0 here. This would now work because the end result of this expression here could still be null. So if this here is null, then this part of the code would not be executed due to this operator. So this whole result here could be null, but comparing null with a 0 is a perfectly valid comparison, because null is not the same as 0, but this result of that would be true again. So we could do it like this, or we could again chain another call with another question mark dot equals to compare this with another value. And this is now the same as the double equals operator, just that we can also use the question mark dot operator before. So we could say equals 0. If we now say input as integer, we say is even like this. Now it will print is even true for an even number. It will print is even false for an odd number. And it will print null if it actually can't do this calculation because we did not enter a valid number. And I know that all this can still sound a little bit confusing to you, especially if you're completely new to the programming world and why we have all those function chains, what all those empty parentheses mean, this question mark dot operator, why we suddenly have to write these modulo and equals operators here as real function names. If that's not fully clear yet, don't worry, it will get clearer when we get to functions in this course. But this operator is indeed quite important and quite helpful, which is probably the most commonly needed null safety operator in Kotlin. That's how we call these. So you've learned about the question mark : operator, where we can just assign a certain default value in case the first part of this operator is equal to null. You've learned about the double exclamation mark operator, which simply asserts that the result is not null. And if it's null, then our code crashes with this red text. We call it an exception. I'll also get to that in a moment. And then we have this question mark dot operator here, which you can use to only call a certain function on a variable, for example, like this input here, if that input is not null. And this type of behavior that we have these null safety operators, that's actually something that is not fully unique to Kotlin, but that is definitely special about Kotlin, which is something that not many programming languages have. Because what null safety means is that Kotlin supports these null values on the one hand. So we can have integers, strings that are null, that have non-existent values. But null safety pretty much means that Kotlin will see and make sure that such function calls can only be made on valid objects and not on null values. Because you will notice that if we remove this question mark here, then this would be the normal way how we call such a function, but this would lead to a compile time issue. So we wouldn't even be able to run this code because it could be that this here is actually null and calling a function on a null reference is in the end not possible. On Java, we did not have this null safety mechanism. So on Java, writing code like this here was perfectly valid, but if we called such functions on null objects, on null inputs, then the code simply crashed. So that was exactly the same as if we use this double exclamation mark operator here in Kotlin, that our code would simply crash if that value would be null. That is why it's actually discouraged to use this operator, because we want that null safety. We don't want to have the risk of random crashes in our app because certain integers or other values are null. That's why I could really just recommend you that if you have null values in your code, that you use this question mark dot operator as well as the, I think it's called Elvis operator. I don't know the exact names of this, but I think it's Elvis because if you turn your head, it looks like Elvis. But that operator just assigns a default value here in case the first part is null. Because with these two types of null safety operators, such a crash that we've experienced with the double exclamation mark operator can't happen. But let's actually remove this here because I think this is maybe a bit confusing and the calculation we had before was clearer. So why didn't it actually work? That's something I already went over, but why can't we just say is even input as integer modulo 2 is equal to 0? I've already said that, okay, if this is null, then this would mean null modulo 2, and we can't calculate this modulo operation on a null value. But is there a way to only execute this code if this input as integer is actually not equal to null, so that there is a valid value? And yes, there is, with if statements. Of course, there must be a way for us to only execute certain code if a specific Boolean condition is true. So what we can do is we can say if, and then in parentheses, we actually put the condition, so the actual Boolean value. And if that Boolean value is true, so if input as integer is not equal to null, that's actually a comparison operator that I forgot to cover. This exclamation mark equals operator pretty much just means not equal to. So we have equals, that would mean, okay, input as integer is null. And then the code here in the curly braces would be executed if it's null. But we want to check if it's not null, because then we have a valid value. And if we then take this is even line, cut it out and put it in here, you can see suddenly we don't get this error anymore on this modulo operator. Because that's another feature of Kotlin's null safety mechanism, that if we have such an if condition, and we only enter this code here, if the input as integer is actually not null, then Kotlin is smart enough to know, okay, inside of this code, input as integer can't be null. And therefore, we can perfectly use it for such a calculation, because the code knows, okay, this is always a valid integer number here. And then we can simply move this print line statement in here. Let's actually capitalize that, and then actually use this is even in here. And if we now run this, there we go, please enter a number. We say 5. Then it says, okay, that's not even. If we now enter an invalid number, like hello, then our code simply finishes. So now it does not print this anymore, because this if condition, these curly braces, that's simply not entered anymore, because that condition evaluated to false, since input as integer was null in this last example. And if there is an if condition, then there also must be a way to do something in the else case. So if this condition is actually false and we want to do something in the other case, then we can do this with an else here. Again, opening curly braces, and then the code here in these curly braces will be executed if this condition is actually false and would not enter this if block. So here we could say something like, dude, enter a valid number. And we could of course also nest these if conditions. So we could also go in here and say if is even, which is again a boolean, so we can use this boolean for our if condition. If is even is true. By the way, many coding beginners do something like this, where they say is even is equal to true. That's redundant because is even is already a boolean that is expected here in these parentheses. This way you would just compare whether true is the same as true, which is always true. So don't compare this with true, just pass is even. And then in here we can say the number is even. And we can again have an else condition where we say the number is odd. And then we get rid of this line. So this way we really have a different print line statement depending on whether the number is even or not. So if we run this and we enter a number, we enter 5, then it says the number is odd. So we now have it as a readable language and not just the number, or is the number even, true or false? No, we can really say the number is odd. If we enter an even number, it says the number is even. And if we enter an invalid number, it says, dude, enter a valid number. And by the way, something you can do with booleans that I also haven't covered yet is you can negate them. Because of course, if you have a certain boolean and we want to execute code in this example, if that boolean is not even, so if it's odd, but we've saved the information whether the number is even. Of course, we could do it with this else condition here, which would allow us to print something if it's odd. But let's say we only want to print one case. We only want to print the odd case. So we don't want to print if the number is even. So of course we could remove this, but then we would have this ugly empty if body, which actually doesn't do anything, just in order to be able to have this else condition to print if the number is odd. That's of course not necessary. We can move this in here, remove the else condition, and simply negate this Boolean condition by prepending it with an exclamation mark. So this way, if we run this, then we can enter a 5 and it would print the number is odd. If we enter an even number, it would not print anything because we got rid of the else branch. If you however have an else branch like we did before, then I would always make sure to have the if condition in here non-negated, because it's always easier to understand a non-negated condition than always having to negate it in your head to understand under which condition this branch would be entered. With a simple Boolean, it's easy to understand, but sometimes in the real world, these conditions are not always that easy. A plain Boolean, sometimes you have chain Booleans with logical operators and so on. So I would always try to make sure to negate as little as possible if you use this else branch. The interesting thing about if statements in Kotlin is that we can also use them as an expression. So an expression would, for example, be something like this, something that we can assign to a variable. So what does that mean? We could, for example, go ahead and say val output, and we set that variable equal to if input as integer modulo 2, if that's 0, then we say we open a body and we simply phrase a string here. We say the number is even, and in the else case, we say the number is odd. So this output is now a string. If the input as integer is even, then this string is assigned. And otherwise, this string is assigned. So we could now go ahead and get rid of this if else here and simply say we print this output. And if we run this, enter an even number, it again says the number is even. If we enter an odd number, it says the number is odd. So if you have a certain condition, and if the condition is true, you want to assign one value to a variable, and if the condition is false, you want to assign another value, then you can just use an if-else condition here as well to just assign that to this variable. Of course, this is now a case where you have to have this else block, because if we get rid of it, the code doesn't know, okay, but what if this condition is actually false? What value should I then assign to the variable? The variable, of course, always needs to have a valid value. If this condition is false and you say, okay, in that case, the variable should be null, you would also need to specify that by saying else null. So then if the condition is true, this value would be assigned, and if it's false, null would be assigned. But this would of course now mean that the output could be null, and that's why we get this question mark again after the string. So we would need to have all these null checks again, in this case, if we wanted to do something with this output. Here, none of these null checks are actually necessary, because if we pass null to the print line function, then it will simply print null in the console. So that is a valid output also for a null value. Sometimes, however, you also have multiple if conditions and not just an if or an else. In these cases, you can also make use of so-called else if conditions, which simply comes in between, and you can have as many as you want. Well, in this case, it wouldn't make sense to add an else if here as a third condition, because for this input as integer being not equal to null, there are only two valid scenarios. Either it's null or it's not null. But imagine we want to check whether the input as integer is actually a specific number. For example, here we could say the number is even. If the number is odd, then everything afterwards will be executed. But we could check, okay, if the input as integer is actually less than 10, for example, then we say the number is odd and less than 10. And then we can have an else condition where we say the number is odd and at least 11. So I think you get the idea how this works. If we now enter an even number, it says the number is even because the initial if condition, which is checked first, will be entered. Then if we enter something like 15, it says the number is odd and at least 11. That's correct. And if we enter something like 5, it says the number is odd and less than 10. And as I said, you can have as many of these else if conditions as you want. So you could just go ahead and say you have another one here. And then, oops, the else should be here. And then simply map another condition to some kind of other string. However, in most cases, you actually want to avoid these else if conditions because it's quite hard to read, because you always have to jump into these specific parentheses here. For these scenarios where you have multiple conditions, what's oftentimes much more appropriate are so-called when expressions. When expressions are in the end the same idea as if conditions, but they add a little bit of syntactical sugar to it. So they make such long if else chains a little bit easier and better to read. So what we could do is we could say val output is equal to when, and then open curly braces, and then we can put all of our conditions here in one single line kind of. So if the input as integer modulo 2 is 0, then we add such an arrow. That is how these when expressions work. And we will say, yep, the number is even. If input as integer is less than 10, we would say the number is odd and less than 10. And in all other cases, we can also use the else condition here. We would do this. So this would now be the equivalent code than what we had before here with all these else ifs, if, else, which is much more readable because on a single glance we can see which conditions lead to which result. If you need to execute more code here and not just assign a single value, then you can also open a block of code here via these curly braces. And then you could also do something before printing something, for example. That's one way how we can use when expressions. So let's get rid of this here. This becomes a bit messy otherwise. Another approach that we can stick to with when expressions is one that doesn't work here. So if the conditions are very different, so we use the modulo once, then another time we check if it's less than a certain number, then we use the else block. Then we need to do it like this with these curly braces. But what we can do is we can also pass our input as an integer here inside of these parentheses of the when expression. And then we can directly pass the result we want to check for here instead of this condition. So we could say if that input as integer is 3, then we say the number is 3. If that is 5, for example, then we say the number is 5. We could also check for certain ranges with the in operator. So we could check if the number is in the range of 10 to 20. Then we say the number is between 10 and 20. We could also check if the input as integer is equal to null. We could move this out of this if condition here and then say, okay, if it's null, then we say, dude, enter a valid number. And in the else block that currently doesn't make sense, I have no idea what to print, for example. And then we just say, okay, print line, we print the output. Every single condition of this output evaluates to a specific string. So the output is also a string in this case. If we run this, then we can still enter a number. For example, hello, this would result in dude, enter a valid number. We could pass 5, the number is 5. We could enter something like 15, and then it says the number is between 10 and 20. What's important to understand is that these when branches here are evaluated one after another. So this one first, then it will check for this one and this one and so on. So that means if we would make this range here, for example, starting from 4, we rerun this and we enter 5, then it prints the number is 5, even though this condition would also be true. But since the 5 is checked first, that will be the string that's assigned. And of course, you also don't have to use the when expression to assign the result to a variable. You can also remove this and just check for a certain value in order to execute some code. In this case, it of course doesn't make sense to just map this to a specific string, but rather than use this these curly braces to print something, for example. That would also be totally valid. But if you need to assign something to a variable that depends on lots of different conditions, you can use when expressions. Okay, putting a check to when expressions, getting to the next concept. And that's something we've already faced, specifically exceptions. Exceptions are a mechanism to kind of intentionally break our code if an exception happens. So if something in our code is happening that we can't explicitly handle, so we need to crash our program. And the exception that you've seen is that we can use toInteger, which does give us a non-nullable integer. So here, the toInt function returns a normal integer without this question mark. So this input as integer now can't be null anymore, which is also highlighted here by this yellow warning. But that, of course, still doesn't keep us back from putting in invalid numbers in our console. And once we did that, just a little recap, we enter hello here, then we get this exception. And specifically, this exception is a number format exception. So you can see there are multiple different types of exceptions, of things that could go wrong in our code that would crash our code. In this case, it's, well, formatting a number. We can't parse a hello string into an integer. And what every single exception also gives you is a so-called stack trace. So it gives you a list of all those functions that have been called that helps you to understand how your code actually got to that exception. And these functions that have these gray links, those are actually internal functions that we did not write, that were still called in some way. But these blue links are usually the interesting ones because these link to our own files. And if we click on this blue link, then we actually get to the line that caused this exception, which is this one here, obviously. During the attempt to parse the input to an integer, our code crashed. Now, exceptions will only lead to a crash if they are actually uncaught exceptions. So if we don't stick to further measures in order to prevent these exceptions from crashing our code. If we know that this could happen in certain parts of our code, we can, of course, make sure to handle the case when a specific exception happens. And that works via try and catch. So instead of always just being super confident to parse this into a non-nullable integer, we could also cut this and say, want to try something, want to try parsing that to an integer, but in case an exception is thrown, we can catch it with this catch block that must come afterwards after this try block. So this catch block here, we want to catch number format exceptions. The AI is already suggesting that. So number format exception, and then here, this code is now executed if any code inside of this try block actually throws a specific number format exception. Then we could say we map this to some kind of default value. So that of course must be an integer now because we also want to have an integer in the end. But now we still have a non-nullable integer. We don't need the null checks. We can get rid of this null here. And if we launch this and actually enter hello, then it says, I have no idea what to print because these first three conditions weren't true because the number was mapped to 0 and 0 wasn't covered here. So it went into this else branch. So this is how we can just catch these exceptions. So if you know that certain code can throw such exceptions, that exceptions can happen in a certain part of the code, then it often makes sense to put this into a try and catch block if you don't want this exception to crash your code base. And if you're using some kind of predefined functions like this toInteger function, hovering over that often already gives you here the different exceptions that it could throw, that could happen here, at least if this function is well documented. And it also says when this specific exception would be thrown. So if the string is not a valid representation of a number, which is exactly the case with a hello string. There's also an option to actually have a so-called finally block afterwards. Not so often needed, also not very basic anymore, but the finally block just makes sure that this piece of code is definitely executed, even if an exception was thrown. In more advanced applications, this can then be used to, for example, clean up certain resources, close some network streams, close some file streams, but that's nothing we deal with here, so we can get rid of that. You can also catch general exceptions. So if we make this a normal exception, then this would include all kinds of exceptions that could be thrown, and this block would be executed for any of these. If we specifically say number format exception and a different exception is thrown, then this catch block would not catch it. If we want to erase or throw such exceptions in our own code, that works via the throw keyword. So we could say throw an exception at a given point when we notice, okay, we are at a point in our function where we maybe received some kind of invalid input parameters that we simply can't do anything with. So we need to tell the part of the code that called this function in some way that was an invalid input, just as one example. And we could say, dude, what the fuck did you pass there. You can see we also get a big yellow wall of warning here, because if we execute this, then enter a number 6, and then immediately our code will crash with our own custom exception. Because the moment we throw this exception and don't catch it, the IDE is already smart enough to know that this code afterwards can't be executed anymore. So this wouldn't be a typical use case that we throw the exception directly here in the main function and don't catch it. Rather gets thrown somewhere deep down in other functions. We get to the function stuff later in this course. I know I've talked a lot about functions already, and it's quite difficult to not mention these with these basic examples, since they're pretty much anywhere. Then once you understand that, it hopefully also makes more sense when it could make sense to throw such exceptions yourself. Okay, that was already a lot of possibly new concepts for you. Let's get to the next one. And for that, I really want to get rid of all this code here. So we start off with a fresh new idea. We don't get confused with what we've written so far, but what actually if we want to bundle some related values. So let's say we have some kind of favorite numbers, so multiple numbers. How do we do that? How do we store these? Because so far we've only dealt with single primitive variables that we could assign some specific number to a variable, that we could use floating point, double numbers, that we could pass strings, but it was always a single value. What if we want to bundle multiple such values? Well, and that is where we come to another primitive data type called arrays. An array is in the end a fixed container that we can use to store multiple pieces of the same data type in. So for example, we can create an integer array with integer array of, and then in here we can input all kinds of numbers. So you can see with this notation, it expects a var arg, a variable number of arguments of type integer, and we could just pass in our favorite numbers. I don't know, 1, 2, 3, 69, I don't know. And this way, we can bundle all these numbers here in a single variable. If we now hover over this, we see this is now an integer array. And if we now want to access certain values inside of this array, so let's say we want to print the second element of this array, then that works via indexing. So the way arrays work is every single number gets a specific index. In coding, we start counting from 0. So the first number would be at index 0. The second one would be at index 1, index 2, index 3. So we could say we print favorite numbers, and then we can access the favorite numbers array at a specific index with these square brackets. So we could say favorite numbers at the index of 0 would then take a look at this array. Which number is actually at the index 0? Since we start counting at 0, that refers to the first number. So if we call this, or if we execute this, you see this prints 1. If we set this to 1, it prints 2, since at index 1 we have the number 2 stored. If we set this to 3, it prints 69. If we set this to 4, it throws an array index out of bounds exception. So you can see that's another type of exception that could happen. Because if we only define 4 numbers and we try to access the index 4, which corresponds to the 5th element, since we start counting at 0 again, then it tries to look there, but it notices there is no 5th element, so something needs to happen. In that case, it will crash. So we could either do this and put this code in a try and catch block if we were unsure whether this element exists, or we could also use an alternative way of accessing an element by saying get or null. We pass in an index, and if this index actually does not exist in this array, it will simply return null. So if we now do this, it says null because the index 4 does not exist. And if we now, again, have some kind of input that we want the user to pass in, and then we access the number at the given input, well, then we need some more safety measures because the user could enter anything. We can then say again, input as integer would be input.toInt or null to not make the code crash if something else is entered. Then down here, after specifying our favorite numbers, we could say if our input as integer is actually not equal to null, then we could say your number is input, favorite numbers at the index. So we can also say dot and then refer to these square brackets. Then it will replace this whole thing with this curly braces, so we can have this as a proper placeholder and don't need to type these around. If we then say we want to use this input as integer here as the index, that works, then that still doesn't prevent us from putting in something like 5. And there is no index 5 since our array only has a length of 4. In order to make this a bit safer, we could also add a check. So we say and our input as integer is actually less than the favorite numbers dot size. So the size here is actually the number of elements we have in this array, so 4. And if our input as integer is less than 4, so at 3 at max, then that would already make sure that we can't access an index that is 4 or larger. So we could also add an else condition here where we say that index doesn't exist. If we run this, we pass something like hello, it says that index doesn't exist. And if we run this and pass something like 5, it also says that. If we pass something like 3, it prints your number is 69. However, if you look at this, there is still a way for us to break this code. And that also gives you an idea of how careful you sometimes need to be when writing code. Because what happens if we rerun this and we enter something like -1? Then our code crashes again because -1 is a valid whole number, but there is no number at the index of -1. So that's important if you become a developer, that you always think of these kinds of edge cases and really try to intentionally break your code, of course, during development. Because if you think of it from that angle, then you also know what kinds of preventive measures you need to take in order to not break your code and in order to not make your code break when a real user uses it. So in order to avoid this, that our code also crashes for negative values, we not only want to check whether the input as integer is less than our size, but also that it's at least 0. So we could say if that input as integer is in a range of 0 up to, so that is how we define this range with a double dot, is in the range of 0 to, and we could now say favorite numbers.size, but that won't work because the last, or the right side of the range is including. Favorite numbers.size is equal to 4 since we have 4 elements, but there is no index 4. The highest index is 3. So we would need to use the last index variable here instead, since that refers to the highest index that is still valid. And if we now run this again and we enter -1, it says that index doesn't exist and doesn't crash anymore. What's important to know about arrays is that they have a fixed size. So the moment we define this array, we can pass a dynamic number of numbers here, or of course, we can also create other types of arrays. So there's also float array of, there is double array of, I think that makes sense. There's also a generic array of, where we can pass any type of object, for example, strings. Here's Boolean array, byte array, and so on. So lots of different data types. But what all these have in common is that they have a fixed size. So we can pass a dynamic number of arguments here, but the moment we create this array, we can't dynamically add a 5th number anymore if we added 4 before. Technically, what we could do is we could say +5. So the plus operator also has some sort of behavior for arrays. If we do this and rerun this, pass in 4 here, it will actually give us the number is 5. So in the end, what the plus operator for arrays does is it does add the number to the array. So this is the equivalent to this, but still, once an array has been created, its size is fixed. So what effectively happened here is when we wrote +5, it first created an instance of this array having a size of 4, but the moment we add 5 as another element, this under the hood created a completely new array. So technically, 2 arrays were created here. First this one, and then another one in order to include the 5, because the initial array size did not have enough space to fit in the 5th. So a new array needed to be created in memory that does fit in that 5. And in programming terms, we also say that an array is immutable, at least in regards to the amount of elements we have in it. It's not immutable in the sense that we can change the numbers that are already in the array. So we can say favorite numbers at the index of 2 and also set that to something like 69. And if we run this and say we want the index 2, then that now says 69, because here with this line, we've accessed the array at the index of 2 and updated the value. So this way arrays are mutable. We can change the single numbers once we've created the array without needing to recreate an entire array. But we can dynamically add more numbers. So what do we actually do if we want to dynamically add more numbers? Let's say we actually want to ask the user 3 times to input a number, and then we give them back maybe the sum of all these numbers together. Well, that would still be possible with just 3 specific input variables here. But what if we don't yet know how many numbers we need to add in order to fulfill a certain condition? For example, we want to let the user enter new numbers for as long as the sum of all these numbers is less than 20, for example. Well, since we don't yet know which numbers the user will enter, we also don't yet know how often we need to ask for this input. And we can't also easily increase the size of such arrays in order to maybe store these numbers together. Wouldn't be needed specifically in this example, but would be one way to solve it. But maybe imagine you just want to track all the numbers the user enters, maybe 10 numbers or so. You of course don't want to put 10 of these read line statements here in your code in order to collect all these numbers. What I'm trying to get to are loops. So if we need to do certain things repetitively, then there is no way around loops in programming. And with loops, I will also get to a different data structure here in a moment that is a bit more dynamic than arrays. And that doesn't mean that arrays are bad. That just means that in certain scenarios, I'll get to in a moment, another data structure might be better, and in some other scenarios, an array might be best. But let's actually do exactly that. We want the user to, let's say, enter 5 numbers. Or even better, we want the user to enter a number, how many numbers will follow, because then it's definitely dynamic. And then after the user entered all those numbers, we answer with the total sum of these numbers. So how does that work? So first of all, we need to ask for the amount of numbers, which is readline. And we can also convert this to an integer or null. And here in this case, I would say we use the else operator to just return 0 here. So if this is invalid, then we just say, okay, the user does not want to enter any numbers if they enter some kind of hello string again. And now, depending on what this amount of numbers is, if it's 5, then we need to answer with 5 calls of this readline function. So the user can have the chance to enter 5 subsequent numbers. If they enter 7, then we want to call this 7 times. And this is something where we have to use loops. And there are different types of loops. The easiest to understand is the so-called while loop. So we have a while loop, which in the end just works exactly the same as an if condition. So we need to pass a certain Boolean condition here in these parentheses, with the difference that the code that follows afterwards is not just executed once, but for as long or while the condition is true. So it will check if the condition is true. For example, we declare a counter variable, which is commonly used. So an I, which is the current iteration of this loop. Let me quickly enter this, and then it will make more sense when I explain it. Then we say while I is less than amount of numbers, and then we say I++. So what the heck happens here? So we declare a variable, which we can increment, which we can change the value of, called I. That's just a typical name for a variable that we use in loops as the counter variable. It starts at 0. And now for the condition we say, for as long as I is less than the amount of numbers, for as long as that condition is true, we execute this piece of code. So if amount of numbers is 3, for example, then the while block will check, okay, is 0 less than 3? Yes, that's certainly the case. So this code will be executed. At the end, I will be increased from 0 to 1. After it executed this code, it will again check this condition now, but now with the value of I being equal to 1. So it will check if 1 is less than 3. Still the case. So it will execute this code a second time. Increment I to 2. It will check, is 2 less than 3? Yes, still the case. It will execute the code a third time. Increment I to 3 now. Check this again, is 3 less than 3? No, that's not the case anymore. So it will exit the while loop and go on with the code that follows afterwards. So with this condition we achieve that this code here gets executed 3 times if amount of numbers is 3. If amount of numbers is 100, then this code will be called 100 times. And that's now exactly what we want. So we can go in here and we say, val number is equal to readline dot toInt or null. And now we of course need to think about the scenario again that the user enters an invalid number for one of these. So just a string that we can't directly parse to an integer. For example, we could again say that in this case, we want to simply add nothing to our sum. but we will still count it as a valid input, or at least as an input that is considered under this amount of numbers. And then we need some way to actually keep track of the current sum. Since we want to sum up all the numbers the user enters, we need to keep track of the sum. And that works with a var sum, for example, that initially is 0. And with every single loop iteration, we now take this number where we listen to what the user enters, and we add this number to our sum with plus equals. And then after that, we can say the total sum is $sum. Let's try this out. And let's maybe also prepend a little print line statement here. How many numbers will you enter? Like this, and we run this. How many numbers will you enter? Let's say we enter 3 numbers. Hit enter. Okay, now it expects the first number, which let's say is 50. Second number is 34. And the third number is 20. And then it says the total sum is 104. And in this while loop, we could of course also add more print line statements so that we get a bit more information by saying print line, please enter number. We say hashtag and then have I plus 1. So since I starts at 0, in the first iteration, we would say, okay, please enter number 1. In the next iteration where I is increased, it would say, please enter number 2 and so on. You will see how this works. How many numbers will you enter? We say 10. Then it says, please enter number 1. And we can really have any type of amount of numbers here. And it will ask for 10. And once we enter the 10th number, it will give us the total sum of all these numbers. Now, something we can do in loops is instead of returning a default value here, so if we would enter, let's launch it again, if we would enter something invalid here, so first of all, we say we want to enter 2 numbers, then for the number 1, we enter hello, which is not a valid number, and for number 2, we enter 5, well, then the total sum is 5. So it simply ignored this number, but still took it as a real attempt to enter a number, since we just mapped this number to 0 in this case. If we don't want this, and we should just ignore all attempts from the user where they enter invalid numbers, we could instead say continue. That's a keyword that will simply immediately jump to the next loop iteration and not execute the code afterwards anymore. So in this case, we would again immediately jump to the next evaluation of this while condition without having incremented I before, so I is still what it was previously, and therefore it will ask for the same number again. If we relaunch this and we then enter 3, and we enter something incorrect for number 1, then it will ask for number 1 again until we eventually enter something valid, and then it will proceed with number 2, and then prints the total sum again. Alternatively, there's also the break keyword, which will completely break out of the loop. That's not what we want here, because then no more iterations would be executed. So continue makes more sense in this scenario. But what now happens if we want to just print all the numbers the user has previously entered? Because right now we can simply sum up this single sum variable here that's just a single value. But if we want to give the user all numbers and we don't yet know how many numbers they are about to enter, we need a bit more of a dynamic data structure. So arrays would technically work. So we could say var numbers is an integer array of initially empty, and then in every single iteration we could say numbers plus equals number, and then we can say all your numbers are here. You will notice that if we say numbers and we try to print our array, that itself does not work. If we say 1, 2, 3, then it will give us some kind of weird gibberish, because arrays can't be printed like that, but we can call the, what is it called? Content to string function, for example, which will print the content as a string. So if we say 3 and we enter 1, 2, and 5 or 6, then it says here are the numbers 1, 2, and 6 in form of such an array. That does work. But as I said, with every single call to numbers plus equals number, we create an entirely new array, which is not always very efficient. Because a single array has a fixed size, and if we want to increase the size, that means we need to allocate a new array in memory. A more dynamic data structure are so-called lists, specifically mutable lists. So if we don't make this an integer array, but a mutable list, then we need to define what types of elements this mutable list contains, which we do with these angle brackets. So we want to store integer variables here. Then we also don't need to make this a var anymore. And then we can say numbers that add, and we simply add the new number. And lists we can also easily print just like that, so we don't need to call this function. This is now a better approach because with a list we can dynamically add more elements without needing to recreate the entire list. So we could say, want to enter 10 numbers. And we just enter some kind of numbers, and at the end it will then give us a list of all those numbers that we've entered. So I think this is clear how we can use this while loop in order to just execute certain parts of our code as often as we need, depending on a specific variable, for example. But especially if we have a loop that looks like this, where we have a specific counter variable, which is just needed here in order to execute this loop amount of numbers times, then there's actually a better alternative that is a bit more concise. And that is the so-called for loop. With the for loop, we actually intend to loop over something in the end. So if we already have a set of values, and for each element in that set of values, we want to execute one loop iteration, then a for loop is typically what you need. And this set of values can also be a range after all. So what we could do in order to write this equivalent code, but with a for loop, we could say for I in 0, and we create a range up to amount of numbers. And this is now again dangerous because then the last value is including. If we start at 0, then we will actually have one more iteration than we need. So we could either make this a range starting at 1 to amount of numbers, or we say 0 until amount of numbers. So until, you can also see it here, actually excludes the last element. We typically start looping from 0, since that is also the first index in lists and arrays. So we can also just access the list elements via this indexing approach we know from arrays. And since they start at 0, we typically also start counting from 0 in loops. In this example, it's not needed since we don't use this I to index something. But then we could really just take this here, actually without I++, move this code in there, get rid of that while loop, get rid of that I, and now we have the equivalent code. But the for loop actually bakes in this counting up in these parentheses here. So with a for loop, we don't execute this loop anymore while a specific condition is true. This in here is not really a condition. But with a for loop, we specify that we have a certain element which changes iteration after iteration. And this element will take the values, in this case, from this range. It will start at 0. In the next iteration, it will go to 1, to 2, to 3, and so on, for as long as it's less than amount of numbers. So here, this will now achieve the same result. We want to enter 3 numbers, for example, number 1, 3, 6, and 9, and then it gives us all these numbers, which is now exactly the same. It's less code than before, as you can see, but the for loop can't only be used to actually have such a counter variable, like I in this case, to count from a specific range here, but it can also be used to immediately loop over a list, for example, since a list is also some sort of range because it just contains a specific set of values. So let's say we actually don't want to print these numbers here in a single line, but let's say for every single number, we want to have its own dedicated print line statement. So what we could do is we could say we have for every single number in our numbers list. Then this number is now not starting at 0 anymore, but the first iteration will be the first number in our numbers list. So if we now say we print this number, relaunch this, we say we enter 3 numbers, 5, 12, and 56. Then we get all those numbers printed in their own line because we took this list and we iterated over it. And in each iteration, this number will just jump to the next number. So in the first iteration, it will be the first number in the list, and the second, it will be the second, and so on. And in technical terms, we call something like this an iterable. So something we can iterate over. And there are multiple types of iterables in Kotlin. So lists are one of them. Arrays would be an iterable. Interestingly, a string is also an iterable. So what we can do is we can say enter a string. We then receive this input. Now we don't need this null check here because we're not converting this to an integer anymore, but we want this as a string. And then we could say for character in our input, and we print this. If we do this and we say hello world, then every single character of the string is printed in its own loop iteration, because what a string really is under the hood, it's nothing else than an array of characters, an array of simple letters, numbers, and anything you can type on your keyboard. And since a string is just an array under the hood, we can also iterate over it. And that also means that we can access a string at a specific index to get the character at that specific index. So we could do something like I, which again corresponds to an index now, in input that last index, and now this range goes down to 0. So that's something we can do in Kotlin, that we start the loop iteration at the last index of the string, so at the index of the last character, and then iterate down to 0. So if we now actually say something like, well, final string, and we can use build string here in order to dynamically create strings. You don't need to worry about this more at this point, but we can really just move this for loop in here. And with this build string function, we can now construct our own strings dynamically by saying we want to append a specific character, and the character is simply our input string, so the original string, and we access it at the index I. And since we loop from the end to the beginning now, you maybe can guess what this will lead to, because if we now print the final string, hit run, then we can say hello world, hit enter, and it actually reverses that string. That is something we could of course do with a loop. So we really just loop from the last character to the first character, and for each character, which starts here at the last index, we append this to the first index of this new string, which we then print. Alright, so what I now mentioned quite a lot already are functions. So we've already talked about the main function, which also has this function keyword here. We talked about this readline function. We had this toInt or null function. And as you maybe already noticed, what all these functions have in common is that they have these parentheses at the end. Sometimes empty, sometimes we have some sort of input there. So let's dive a bit deeper into what a function actually is and how we can create our own functions in Kotlin. So in the end, a whole program is something that takes certain inputs and delivers certain outputs. And a function is actually the same, just on a lower level. So of course, if we wrote code like this that reverses a string, then in a bigger application, it might happen quite often that we actually need to reuse this code at lots of different places in our overall program. And it would of course be quite bad if we always had to write this build string for append at each place where we need to reverse a string. Not only because our code base will grow a lot in size, but also if there is an issue in this code, then the issue has to be fixed at all these single places in our code base where we use this code. What we can instead do is we can define a function that defines, hey, this is how we reverse a string, and then we can easily just call this function in a single line of code wherever we need it. So let's see how this could work. A function is actually not declared here inside of main anymore, because main is its own function that gets called when we launch our program. But the signature, how we need to write such a function, is actually the same as for this main function. So we can go below main here and declare a function with the function keyword, and we call it something that describes what it actually does. For example, reversed, by taking a string and then reversing that. So this would now be the equivalent signature as we had it here for the main function. But the thing that is now different for our reversed function is that it actually needs an input, because of course it needs to know the string that we want to reverse. That is something that can of course differ between function calls. The logic that then decides about how a string is reversed, that is always the same. But which string is reversed, that is something that can differ. So we somehow need a way to pass the string that we want to reverse to this function. And that works inside of these parentheses. So we can pass our string, that's the name, and we need to specify the type here. So here we can't omit this anymore like we did for variables, because we don't yet assign a clear value here, which Kotlin could then use to infer the type. We just say, hey, we need to be able to pass in a string of type string. So this could also be some sort of other name, string to reverse. That's really just the variable name that we can then use inside of this function in order to reference the string that we've passed to it. And then we can really take our code, this build string function, put this in here. Then we of course don't have access to input anymore because this function is now in a different scope. That's how we call this. So here at this point of our code base, this function has no context on what happens inside of the main function. It only has context to what we actually pass to it. And if we want to then reverse the string that we put in via this readline function, well, then we need to take this input and later on pass it for this string to reverse. And inside of this scope of this reverse function, we then take this and replace it for our input, because that's the variable we have access to here. And that would then again give us our final string. And we could then print it, for example, and say well, let's just print it directly, string to final string. That's the result. And then instead of all this, we could get rid of that and call reversed. And for the string to reverse, you can see it now expects a string here. We simply pass our input and then get rid of the print line statement here. And if we now rerun this, then it asks for a string. And if we enter hello world, it will again print hello world reversed. But now that we made this a function, we can easily call this as many times as we want. So we can duplicate these lines here and print the string reversed 5 times. So we can again say hello, and then it will print the reverse string 5 times. So this is now really the whole reason why we should implement functions if we need certain code at least 2 times. Actually, not only if we need certain code at least 2 times, but a function can also make a piece of code much more readable, because this way, we just need to read the function name in order to understand what this piece of code does. So we don't need to deep dive into the actual implementation, see, okay, here's a for loop, we loop from the last index to 0, we then append this in some way. What does that actually do? No, by making it a function and putting this code in there, it's super clear, okay, this reverses the string, I don't need to read any further. Okay, but what actually if we need the reverse string here in our main function? So right now, we do print it here in this reversed function. We do see it in the print line statement. But let's say we want to do something with this final string, but want to do something with it in the main function. How does that now work? Well, in the end, what that is, it's an output of this function, a so-called return value. So a function gets certain inputs, our string to reverse. It then does something with these inputs. It reverses it in this case. But then it can also give us a certain output, so the final reverse string. And then the main function can decide what to do with it, whether to print it, whether to do something else with it. So that's a much more flexible approach than just always printing this, because that way we have no access to this final string at the place where we call this function. So how does that work? So if we just specify a function signature like this, then we have a function with a function name that has certain input arguments. By the way, we can also have more here by just separating these with a comma and say, for example, we also want to have a number here of type integer, and then we get an error here because we did not pass a valid value for this number, but we could do so by just passing one here. But that doesn't make sense in this case. But what we need to do in order to return a value is we need to jump after this closing parentheses, say, okay, this is actually the return type. We again get a string back from this function. And now we do get a little error here on the closing curly braces because it expected a return expression. So return is the keyword that we now use inside of a function to say, okay, now the execution of this function is over because we know the return value, we know the output of this function. So at this point, we can return it to where we call this function. And if there is no return expression here in this function, well, then we get an error and we wouldn't be able to run this program. So instead of printing this final string now, we can return it. So we say, return this final string. And now this will still work as before, just that if we run this and we type hello, you will notice that nothing actually happens. So the string was actually reversed 5 times, but we don't do anything with the output of these functions. But what we could now do is, let's actually get rid of these 5 reversed function calls. What we could now do is, if we actually hover over this reversed function, we can now see, okay, it returns a string. So what we could do is, we could say, reversed is equal to whatever this function returns. And that's something we did all the time. For example, with this readline function, that's a function that returns a string value. So if we hover over that, we also see, okay, that returns a string, which is the string that the user inputted in the console. If this would be an integer, well, then we would know, okay, this variable here would also be an integer. And now we have access to this reverse string here in our main function, and we can do whatever we want with it. So we could say, we print it, for example. We could even feed it back into the reverse function. So we could say print line reversed. So we take our reverse function and then pass our reverse string in there. So we get the original string again. Or we could do something like we implemented a little palindrome checker. So if the string is actually the same if it's reversed. So if input is actually the same as our input but reversed with our input, then we say we print that's a palindrome. And if we launch this, and then enter something like race car, which is a palindrome because backwards it reads the same as forward. If we hit enter, then it says that's a palindrome because the input, so race car, is the same as reversing the input. In this case, it would actually make more sense if we take this reverse string and pass it here. Why is that better? Well, because every single call to this function will again loop over the string and reverse it. But if it's about the same string, the same input, then we don't need to reverse that over and over again, but we can just refer to the already reversed string. So we just need to loop over it once, and then we have that as a variable, and we can do whatever we want with it. And that's really how we can write our own functions. Something that is also pretty cool is that we can give our parameters, that's how we call these, default values. So if we say we don't necessarily care about a parameter being passed at all times, we can say, okay, if that parameter is not passed, then we just assign a certain default value. We could do this by just saying that is equal to hello world, for example. If we then actually run this again and we enter just hello, then it will reverse hello. But if we actually don't pass in this input here, so we just omit this parameter, you can see we don't get an error anymore, because in that case, it would simply use this hello world string. So if we would run this again, we enter hello again, in that case, it would now reverse hello world because that's the default value since we did not pass anything to this function call here. Let's put this input in here again. Something else that Kotlin supports and that I can only recommend you to do is to use named parameters. So here where we call our functions, we do pass in our input, but when reading this code here, it's not always super clear representation this input string has in the context of our function. So with a simple function like reversing the string, it's pretty obvious that the input is going to be reversed. But sometimes functions actually take multiple parameters, and then it's not always clear which parameter actually is meant for what. What we can do in that case is we can use name parameters by just taking the parameter name and simply saying string to reverse is equal to string. Because this way it's much more readable to see, okay, this input is actually going to be the string to reverse. So this doesn't have any impact on the actual behavior of our code, but it does make it more readable. So I would only recommend to make use of that. That doesn't work for functions coming directly from Java that you use in Kotlin. So that's a pure Kotlin language feature. But if you have such functions that are just written in Kotlin code, then I would always make sure to use name parameters unless it's super obvious what a specific value is used for in that specific function. Something you've also noticed before in the context of functions, when we actually wanted to convert our input to an integer, then we wrote something like val input as integer, and we set this equal to input dot to integer or null. So you can see that's also how we get all the functions that we could currently call in this context. So this is quite a different way of calling a function, right? Because we had to call a function and then pass the actual parameters to this function here in these parentheses. But what we did before is we took our input, we took our parameter, and then called a function on that parameter with this dot notation. So what is the difference here, and why does it work like this once and like this at another time? Well, that's another feature that Kotlin offers us, and it's called extension functions. So with extension functions, we can achieve that we can call a function on an actual object, on an actual variable, string, array, whatever. And that also does not have any specific changes in behavior. So every single extension function we can also write as a normal function with a normal parameter here in these parentheses. But it does have a difference in regards to readability. And it's actually a really cool Kotlin feature because sometimes it just reads much better if we see something like, okay, input to int or null, or input dot reversed, rather than reversed input. That's not a very human way to say that you want to reverse something. So how would that work to define such an extension function? Well, that works by going to our reverse function, and all we need to do is we need to specify the type of variable or object that we can call this function on. So now we don't need the string to reverse anymore as a normal parameter here in these parentheses, so we can really get rid of that and just have opening, closing parentheses to say, no, we don't have any direct arguments in this function. But before the function name, we now say, this function can be called on strings by saying string.reversed. And we could still specify more arguments here. So we could still have a number again, for example, which we could use here. Obviously, we can only call a function on a single type of argument, but if we need more parameters than that, we can pass these here in the parentheses. In this case, we only need one parameter, which is the string we called this function on already. So this is totally fine to not have any arguments here in these parentheses. But now we get some errors here because we don't have this clear string to reverse anymore. So how do we now reference the string that we called this function on inside of this function? Well, and that works via this. So this is a keyword in Kotlin that we can use in different contexts, but in the context of an extension function, this refers to, if we tap this refers to the string that this function was called on. So what we could do is we could say this that last index and this at the index of I. And for some of these calls to this, we can actually also omit this. So if we remove this here, you can see we can still reference last index because this is implicitly added by the compiler. In some other cases, like using such operators based on this string, so the array index operator would also be called an operator. Here we can't omit this anymore because this is quite a weird notation and it wouldn't know which specific object it should refer this index to. So here we do need this. But for all kinds of calls or referenced variables on this object, on the string specifically, we can omit this. So if we now have this function like this, we obviously can't call it like that anymore. But what we can do is we can say we use our input and we call that reversed. There we go. That's our function. And if we again call this, enter a string, something like race car again, then we don't get any outputs. What did I do wrong? Let's first of all remove this input as integer, but that was unused anyways. So we have our input. That is the console input. We then take this input, we reverse it. And the fact that we did not get any console print line statement, but somehow an empty line, tells me that this reverse string is actually empty. Let's investigate why. What's kind of odd is that it marks this string here as gray, that it says receiver parameter is never used. So this string that we call this function is never used, even though we referenced this. And I can already spot the issue here, and that goes a bit more in the advanced Kotlin direction. But the thing is that this can be called in multiple contexts, as I said. In the context of an extension function, it references this string. But there's also another type of function, which is actually this block of code here, which we'll get to later in this course. So I don't want to get into that and mix this with these normal functions now. But let's actually go to this and say this at reverse. Because with that, we make sure that we actually reference the string we call this on so that we refer to the string in the context of this reverse function. You will understand this better later. But if we now run this again and type race car, we again get an empty output. Because we also need to do this for the last index. Because otherwise, this that is implicitly added, again refers to the context of this build string function. Sorry for that. If that is a bit confusing right now, it will make more sense later on when we talk about Lambda functions. But for now, let's rerun this once more and then putting in race car. And yes, now we also get the proper string that this is a palindrome. So that's something you need to take a bit of care about in extension functions. But other than that, they are really great because you can literally extend any type of variable or object with specific functionality. And then you can just call it like that. And you'll also notice that strings and integers already have a bunch of predefined extension functions. For reversing a string, there is actually also already a predefined function, so we don't need to implement something like that ourselves. It still helps, of course, to understand loops like we did here. But if we actually type input dot, then we can see all those functions that can already be called on string objects. So if we scroll down, for example, we can filter certain strings. We also get to that later. We can format it. So if we have certain placeholders, we can convert a string to lowercase letters. I don't know, we can replace certain characters in the string. And I think there should also be a reversed function in strings. I think we don't see this right now here because we do have our own reversed function, which kind of overrides the other reversed function. But we could test this by removing this one. And we say reversed. You can see there is still this reversed function, which now comes from the Kotlin standard library. So that's the pool of functionality that Kotlin already offers as a language. But let's put this back again and talk about one last concept, at least one last concept that I want to talk about here, in regards to functions at least, and that is function overloading. So what we can do is we can overload a function to make it callable with different types of input parameters. So right now, we can reverse strings. But what about we have a number, so an integer, and we also want to be able to reverse integers? Well, right now, if we have an integer, and let's just say we convert this, to an integer, and we want to be able to reverse that integer number, but you can see we can't call this reversed function on it because this reversed function can only be called on strings. How can we extend it to be also callable on integer? Well, that works via function overloading. So if we overload this function with another implementation that works for another type of argument, another type of parameter, well, then we can also call it on that type of parameter. So we can go down here, we can say, we also want this function to be callable on integers, call this reversed, gives us, in that case, an integer. And here we could simply say, return this, so the integer, dot toString, so we take the integer and convert it to a string. This direction we haven't used yet in this course, but that of course also works if we have a number, an integer, and we want to just interpret this number as a string. This is less error prone than the other way around because every number would be a valid string, but not vice versa. So we can convert this to a string. And on this string, we just call our existing reversed function on from above, because now we have a string, which we could then afterwards interpret as an integer again. But now, here, if we have such an input as an integer, well, then we could also say input dot reversed. That now works. And to show you that this is now a real reversed integer number, we could also do a calculation. We could say, okay, our initial input plus the reversed input. Let's remove this one here, and we run this, and we enter something like 45, and that gives us 99, because 45 plus 54 is 99. And the same concept of overloading functions also works if you have normal parameters. So if the string would be a normal string parameter here, and we reference this in the function like this, then we could also properly overload this function here with a number. And then we would reference this number instead. So this also works. Something that doesn't work is to overload a function with the same signature, so with the same set of parameters and return values. So if we now said we want to have a reversed implementation with a different string, so string 2 for example, and we also return a different string, well then the code doesn't know anymore what should happen, which function it should call if we call this with a certain string. What we had before is super clear, because if we call this function with an integer, it knows, okay, this function needs to be called. If you call it with a string, that one needs to be called. But if both of these actually take the same type of arguments, well, what kind of function should it call in that case? It doesn't know that. So overloading only works if every single overloaded function has its own unique set of parameters. Okay, so you now know that there are certain predefined functions like this reversed function we've used before, this toInteger function, and so on. And if we carefully take a look, then we notice that this build string function is actually also a function. But you can see this is actually used a little bit differently than the other functions because it has this block of code, these curly braces afterwards. Why is that? Well, that is because this build string function takes a so-called Lambda function as an argument, as a parameter. So Lambda functions is the next thing we need to talk about. Because in the end, a Lambda function is just a function. It's just some piece of code that we can call repetitively. But the special thing about Lambda functions is that we can pass these functions as a parameter to another function. So why would that be useful? I think it will best become clear if you take a look at the predefined functions from the Kotlin standard library that make use of Lambda functions. So for example, we receive a certain input here in our console. Now let's actually get rid of these functions here because we don't need these at this point anymore. We receive a certain input. We just want this input as a string, and a little recap, every string is just an array of characters, so something we can iterate over. So let's say we now want to be able to filter these characters based on a specific schema. So let's say we just want to remove all digits from the string. Or the other way around, we just want to keep all letters. Well, and we can achieve that with a predefined function, for example. We can say, val letters only, and that's equal to input.filter, so there is a filter function, And you can see here again, we have this pattern that we need to have some kind of a block of code here in these curly braces. And if we take a look on the right, we see the function signature of this filter call, of this filter function that is predefined in the Kotlin standard library. And you can see this predicate argument here, just a normal parameter of this function. This has the type character towards Boolean in some way. So what does that mean? Well, this predicate is in the end a function we can dynamically pass to the filter function. And this dynamic function we can pass has one parameter of type character, so just some sort of letter, digit, or some other kind of character. And this function we pass will then return a Boolean. So this is how we specify this, that we want to be able to pass a function. Because filtering something like a string or a list that has certain elements or an array, that is something that may always happen with different rules. Sometimes you may want to filter a list of numbers based on all even numbers, so you filter out all odd numbers. And sometimes you just want to filter all letters in a string like we do here. So the condition based on which we want to filter is dynamic. That is something we want to leave up to the caller, so to the place where we call this filter function. And that's exactly when Lambda functions are useful. So we can use this filter function, and if we actually take a Lambda function as an argument, as a parameter of a function, then we can omit these opening, closing parentheses here of this function. So we could also add these. This wouldn't change anything about execution, but typically we just leave them away, and I'll leave this block of code here. So this body here, this code we put in there, is now the body of the Lambda function we pass to this filter function. And based on the rule we now specify here, the filter function will apply the filter to this input. So what we could do is we could specify it. With it, we refer to the single argument, the single parameter that this Lambda function actually takes. So this is now called for every single character of this string. And if we take a look in the filter function, this now needs to return a Boolean. If for a specific character we now say we return true, then that means that Boolean will stay in the string. Then that means that character will stay in the string. If it returns false, we will filter it out. So we could say it, refer to the character, and write that is letter. So if a specific character is actually a letter, then it will be kept in the string because this will evaluate to true. If a specific character is not a letter, then it will be filtered out. That's the rule of this filter function. So this block of code is now simply called for every single character in our input string. And for every single character, it will then check, okay, is that a letter? Yes, you can stay in the string. No, I'll throw you out. And if we then print this result, so we say print line, letters only, we run this, we enter a string, and we now enter a string where letters are mixed with some sort of digits, something like this here. If we now hit enter, well, then it will give us hello because it filtered out all these digits. But the same way we can now use this filter function when defining a list or an array, for example. So we can say we have our favorite numbers again. That is an integer array of 1, 2, 3, 69, for example, again. And then we say val even numbers is equal to favorite numbers. And here we can also call this filter function. If we take a look, again, get a Lambda parameter that we need to pass here. This time, the input is actually an integer because our list consists of integers. And for each integer of this list, of this array, we now need to return whether we want to keep this in the list or not. And we can say it, so the current integer we are iterating over, modulo 2. If that's 0, we want to keep that in the list, and otherwise we throw it out. So we can now print these even numbers, run this, and we enter something here, and then it prints 2. Because that's the only even number here in our favorite numbers list. So this way we can really encode this filtering logic in its own function, so we don't need to re-implement that on our own, but we're still super flexible in deciding based on which condition we filter. Something we can also do with Lambda functions when we define these. By the way, we can also define these manually and save them in a variable. For example here, val lambda is equal to a block of code where we say it.isLetter. With the Lambda functions, the type of this function cannot be inferred automatically because it doesn't know what are the inputs of this function, what is the output. That is why we get an issue here because it doesn't know that it is actually a character. But we can fix this by defining the type explicitly, that we have a Lambda function of type character, and then we return, what is it called, a Boolean. And then we can take this Lambda and actually pass it as a normal argument here to our function, to our filter function. So this shows you that this Lambda function is actually not just some random block of code, but it's really just not specifically a variable, but it can be saved in such a val or var. And then we can use this as a normal object or variable in our code and pass this around as parameters to such functions. And what we did before is just the convenient way of creating such a Lambda function so that we don't need to do something like this before. But in the end, this block of code is just to be seen as an argument, as a parameter of this filter function. Something we can also do is we can explicitly give these input parameters, so these characters here, a name. For example, current character, and then have such an arrow which will say, hey, after this point here, this is the actual body of this Lambda function, and then we can't use it anymore. But since we gave this an explicit name of current character, we can say current character is letter. This will be important especially if the Lambda function takes multiple types of parameters. So we can only use this way of referring to the to this current character with it if this is actually the only parameter. So if the function here only takes a single argument and that is a character, or something else, of course. But if there are multiple inputs, then there would be something like character, comma, integer. Then it can't automatically know anymore which of these you now mean with it. So in these cases, you need to explicitly name these, just like I showed you before. So this is why Lambda functions can be useful. But how can we actually use them in our own code? How can we write our own function that takes in a Lambda function? Let's actually take a look at that and implement our own function that filters a string by going down here. So we now have our own filter function. We say we can call this on a string, so we make it an extension function. We call this maybe myFilter to avoid naming conflicts. And then we specify this predicate, which is, you can see the AI autocompletes that, which is a Lambda function that takes in a character as the input and needs to return a Boolean as the output. So whether we want to keep this character or not. And afterwards, finally, it will then return a string, which is the finally filtered string after having applied this predicate to every single character in this original string. So what we could do here, for example, is we return build string again. So here with build string, this Lambda function that we pass, of course, includes the dynamic logic based on which we want to construct the string. That's, of course, also a use case for a Lambda function, since every string is built differently. And here we can then really just say, for every character in this at myFilter, so this now refers to the string here we call this on. Make sure to have this add myFilter. You've noticed the issue before if we don't do this. And then we say if predicate, so we can now use this predicate as a normal function that we can call. If predicate with this current character actually returns true, then that means we want to keep this character. So we can append it to our final output string. Because if we wouldn't want to keep it, we simply don't append it, and then it won't be included in the final output string. We just construct as a completely new string. And then after doing this, after looping over all characters and only appending those for which this function that we've passed returns true, then we return this final string. So what we can do is we can now swap this out with myFilter. Now has the same type of signature here and will work just fine. So we can also pass letters only, rerun this, and it should work just like before. So we can say enter a string, hello, something like this, some numbers again, and then we hit enter, and it will filter out all those digits and leave us with a string hello. And filter is really just one single example of a function that takes in a Lambda function from the standard library. There's lots of functions that are super useful that are included there that you can call on strings, on arrays, on lists, on any type of iterable, to just do something with this iterable based on a specific logic that you pass. For example, another popular Lambda function is map, to just iterate over every single number in this case and map it to a different type of argument. So for example, it multiplied with it. And if we then print even numbers, so that's actually not even anymore, but doesn't matter, let's rerun this. We enter something, then we actually get all these numbers in our original list, but squared. Because map will actually take every single value of this integer array and map the original value, which was it, to it multiplied by it. So we get a new list where every single number is just squared. Just one example for another function that is super useful that takes in a Lambda function as an argument. One last thing to say about Lambda functions at this point is that there is also an alternative way of writing these, because we can also kind of write extension Lambda functions. So just like we can extend a certain type here for our real function, we can also extend a certain type for our lambda function. So remember, if we are inside of our normal function body, then we can reference the string this myFilter was called on by writing this. So this refers to a string here. Whoops, not that one, but this refers to a string, and we can then call some kinds of functions that we can call on strings. And the same type of behavior we can achieve with lambda functions. So instead of passing in this character here as a real argument that we need to pass here inside of these parentheses, we can also make this lambda function extend character. So we can say character dot and then remove this character argument here. We can still technically call this here with a character, putting this in parentheses, but alternatively, we could also call this on character as the object. So character dot predicate. That would now also work because we extend the type character and then the function call follows afterwards. Here we also have this dot just like here, and then the function call follows. However, then we can't reference this with it anymore, because the same rules now count that also count for these extension functions, that if we extend a certain type, we can access the type directly and implicitly. So we can just remove this it in this case, and we can reference isLetter here, because this is implicitly prepended to every single reference here in this function. So we could also say this.isLetter, and this now refers to the current character. So you save yourself of a bit of typing here by not needing this it every time, but every single call, every single function you reference here by default just applies to the current character. And that was also the issue that we had in our previous code with this build string, because this build string is actually an extension function, or the lambda here is actually an extension lambda that lets us directly call such functions on this string builder object here. So you can see that has the same syntax. We have a lambda function. If it returns unit, that by the way means that it does not have a return value. So the function does something but does not have a clear output. But this lambda function is called on the string builder object. And the string builder object gives us access to those append functions, to just append something to that string we're currently constructing. And because in the scope, this refers to the string builder, that is why this previously did not refer to the string object we called our previous reversed function on. So if we have multiple such contexts where this would be appropriate, and we want to reference a specific object outside of the current scope, so inside of this build string scope, we want to reference the string outside of this scope, which also must be referenced with this, then we need to simply use this way of notation here. So this add a myFilter to reference, hey, I actually want this context of this myFilter function and not this context of this build string function. And then we can call this here, we can call all these string functions, since this now refers to the string, we call this function on here. I hope this now makes sense. I know lambda functions have quite a weird syntax if you're new to development, but they are super helpful and quite often needed. Okay, let's put a check to functions. I think functions should be clear. Yes, in Kotlin there are some more special types of functions, but what you've learned here, so extension functions, normal functions, lambda functions, that's really what you need in 90% of the times. And the remaining functions you will stumble over inevitably over time when developing a Kotlin code. But with what you've learned here, you definitely have a super solid foundation in regards to knowledge about functions. I want to remove this again, and I want to clean up everything, because now we get to another big topic, and that is called classes. So if you already have knowledge about object-oriented programming, that is how we call this way of programming that we also stick to in Kotlin, in Java, and lots of other languages, then classes are nothing new to you. If you're new to the programming world, then they will be new to you. Because one use case of classes is to just bundle certain data. Because the use case of classes is to, on the one hand, bundle certain data and then provide functionality that operates on this bundled data. Or in other words, a class provides a blueprint to build something. So for example, we have a class, we specify that with class, and we call that rectangle. Because every single rectangle, you can see the AI tries to autocomplete that, has a width of type integer, and it has a height of type integer. So we can bundle such related data in one blueprint called rectangle. And then we can create a specific rectangle that has a specific width and a specific height here in main by saying, well, rect1, for example, and we set this equal to, now not any random value here anymore, no number, no string, but actually to a rectangle And here in these parentheses, we can then say we give this specific rectangle a width of 5, for example, and a height of 7. And then afterwards in our code, we can print this, for example, with rect1.width and rect1.height. That is how we can now reference this bundled data. So if we run this, you can see it prints 5 and 7, but these two values are now bundled in the same rectangle. So the class declaration itself here is really just a blueprint that tells us this is what a rectangle consists of. But the moment we create a specific rectangle, we call this an instance of this class. And obviously we can have as many instances as we want. We can have as many rectangles that are unique in some way, that have unique dimensions here. But every single of these instances corresponds to the same pattern, that it has a width and a height. And specifically this declaration of defining which data is needed in order to construct a rectangle, because we certainly need to pass a width and a height value in order to have a valid rectangle. There are no rectangles that just have a width and no height. Because this information is needed to construct a specific rectangle, we call this here the constructor of this class. Because what we pass here is needed to construct an instance of this class. So whenever we create a class, we call its constructor with specific arguments. So it's really just a combination of specific values that is needed in order to create a unique instance of that class. But that's really not everything about classes yet. Classes are a huge topic. What we can give a class is effectively a body as well. And in this body, we can now define behavior and functionality that we want to offer for this class. So for example, we can create a variable in here that we maybe call diagonal. So how long the diagonal of this rectangle is. And here we can just apply the Pythagorean theorem. So we say sqrt, that's the square root, a math formula now. I hope you were attentive in math. Then you will know this formula. And here we just say, we take the square root of width multiplied by width plus the height multiplied by height. So width squared plus height squared, taking the square root of that, is exactly the diagonal line length of this specific rectangle. Now we get an error here because this square root function operates with floating point numbers. So we could say we either accept only floating point numbers, so float values for both. Would make sense because it's a valid use case to not only have whole numbers here as a width and height, but also decimal numbers like this. But we could still pass whole numbers, of course. So we can say we pass a width of 5f, of 7f. And then we have a function in here, or a variable rather, that calculates the diagonal of this specific rectangle. So if we say, we have a print line statement, and we say the diagonal is, then we can say rect1 dot diagonal. And this diagonal now refers to this specific rect1. So if we run this, then it says, okay, that is the length of the diagonal of that specific rectangle. Or what we could do is we could define a variable called area, which calculates the area of this rectangle, which is simply width multiplied by height. And then we can say the area is rect1.area. Run this again, and we do get 35, which is exactly the area of that rectangle. And now, since we declared such a blueprint for what a rectangle is, we can also use instances of such a rectangle and require them, for example, as inputs of a function or of another class's constructor. That would also work. So we could go ahead and say function max area, for example, and this function now expects rect1, which is a rectangle here, this one, and rect2, which is also a rectangle, and then returns, actually, let's return a float here, then returns the area of the rectangle of these two that is simply the largest. So we could say val area1 is equal to rect1.area, val area2 is equal to rect2.area, and then we say return max of area1 and area2. So max of is a predefined function. We could also write all this in an easier way, but you get the idea that we could now pass instances of such a rectangle to a specific function, because we've now defined what a rectangle is in the context of our project. Well, let's remove this function here, because I think this should be clear. And let's take a look at what happens if we create another rectangle here. So we have a rect2 as well. Let's also give it a width of 5f and a height of 7f. What we can now do is we can compare those rectangles. So we could say we print whether rect1 is actually the same as rect2. So classes by default are comparable. So if we get rid of this stuff here, and we rerun this, then we get false. Why is that? Those two rectangles are actually the same, right? We gave them the same width, the same height, but it still prints out false. Well, that is because of the default behavior of how class comparisons work in Kotlin. By default, classes are not compared based on their contents. They are compared by reference. So what our code checks here is whether rect1 is the same instance of rect2. And that's simply not the case. Rect2 is its own individual rectangle. It has the same dimensions as rect1, but it is its own individual instance. You can have two red cars after all, but that doesn't mean that both cars are the same. No, you have two individual cars where you and your friend can drive with at the same time. And the same is the case here with the normal class comparisons here. And unless we do something like rect2 is equal to rect1, that would now print true because it's the same instance. And we rather just store kind of a pointer to this rect1 here in rect2 and not our own individual rectangle anymore, then it will return true. But what if we actually want to compare two such classes based on their content? That's something quite common, right? Well, luckily for that, Kotlin has a special type of class. Because if a class is mainly used to hold data and to bundle such data, like the width and the height values, and then just contains functionality that operates on this data, then a class should actually be a data class. As the keyword says, it just mainly contains data. Because if we now rerun the code, then it now prints true, even though both classes are their own individual instance. Because the way data class comparisons work is it will instead compare these classes by fields. So it will check, okay, is the width of this rectangle actually equal to the width of this one? And is the height equal to this one? So if we make this height 8, then the comparison fails because the dimensions of these rectangles are not the same anymore. Data classes also have more cool functionality. For example, if we print the contents of a data class, so we print this rectangle 1, then it will actually print this in a quite human readable way. If this is not a data class and we print this, it rather gives us the actual address in memory where this rectangle is stored without telling us anything about the data contained in that rectangle. So that's another cool fact and perk of data classes. And something that data classes offer us which normal classes don't is a copy function. So what we could do is we could get rid of this here and say rect2 is equal to rect1 dot copy. We create an independent copy of this rectangle 1 with the same values, but now here in these parentheses, for every single value we can pass to a rectangle, we can now decide to change this for this copy. So if we want to create a copy of rectangle 1 and we just want to keep all the values except for a single one, for example, the height we want to now set to 10f, then if we now print rect2, this will give us a rectangle with a width of 5, because that was the width of the rect1 we created a copy of, but the height is changed to 10. So that's also a super, super useful function. And you don't have this function here for normal classes. So if we remove this, then you can see we get an error. And what we could now, of course, do is we could define more classes for more shapes. Let's do that. Let's go down here and let's also have a data class to define a circle. Well, and what kind of data or what is the minimal data that a circle needs in order to be somehow unique, in order to make up a valid instance of a circle? Well, for circles, that's simply the radius. We don't need any width and height values. That's something a circle doesn't have, but a radius. So we make a circle unique based on its radius, and we do need to pass a radius in order to construct a valid circle. And the circle can also contain an area, but the calculation for how a circle area is calculated is now, of course, different than how it works for rectangles. So with circles, that's actually radius squared, radius times radius, and that multiplied by pi. So there is a constant in Kotlin that just refers to the number pi. And for circles, we could also expose something like the diameter, which is simply 2 times the radius. And then up here, we can construct our circle, which is equal to a circle, give it a radius of 5f, for example, and then we print the circle's area, for example. Let's do it like that. We run this, and then we do get the floating point representation of that circle's area. Okay, but what actually if we now want to create a function that does something that maybe sums up the area of multiple shapes? So some areas, let's just pass a list of shapes. And we make this a list of, that is how we declare the list type. And here this now takes in the actual type of elements that we have in this list. Well, alternatively, we could also make use of the var arg notation that you've seen before. So we can pass a variable number of arguments for the shapes. And the type of the shape is rectangle, we can also sum up the area of a circle, right? Together with the shapes of rectangles. But if we make this a rectangle type here, then we can only sum up the areas of rectangles. If we make this a circle type, we can only sum up the areas of circles. But how do we get this together that we allow this function to receive any type of shape? Well, that is where so-called interfaces come into play. An interface, in the end, is just a way to define a contract for a class. So we could say we have an interface shape that just outlines what a specific shape needs to offer in regards to functionality and variables. So we could say every single shape definitely has a radius, an area. And maybe every single shape also has a circumference. Not every single shape has a diagonal or a diameter. So we can't include this here in this shape interface. But you notice that in this shape interface's body, we don't yet declare how these values are actually calculated, because that happens on an individual basis in the class of the shape itself, because that of course differs based on the shape. So when declaring such an interface, that really just says, hey, we have a contract. And if a class says, I want to be a shape, then you have to implement the area and the circumference, because otherwise you're not a shape. So you would violate the contract if you can't implement these specific fields. So that's the whole reason why we have interfaces. And if we now want to make a specific class conform to that interface, well, then we can just organize this a bit better here to make this more readable, not too long. But after this class is constructed here, after this closing parentheses, we can have a colon and then say, hey, I am a shape. And now we get an error, because right now we don't conform to this interface. On the one hand, this area is underlined, but on the other hand, our code says we don't implement the circumference. So it notices, okay, a shape actually has to have a circumference, but our rectangle currently does not implement that. So either implement that or don't tell me you're a shape. And in these JetBrains IDEs, there's a cool shortcut to just automatically implement or come up with implementations for all these fields that we would need to implement to conform to this interface by hitting Command and I. So if we do this, then you can see here's the circumference. If we hit OK, then it will automatically add the code that is necessary in order to implement this circumference. There are a few new keywords here to you. Also, on the one hand, this override. This says, hey, we're actually overriding a field that comes from some kind of higher level, specifically in this case from the shape. And then we have this get here with these parentheses, setting this equal to something. Well, every single field, every single variable inside of a class has a so-called getter and setter. The getter is really nothing else than a function that gets called when we read this field. So when we reference it somewhere in our code, when we print it, then we obviously need to read the current value of that field. And that when that happens, then the getter function of that field is invoked. All that happens implicitly, so without us actually invoking this getter function consciously. But the moment we read a variable or the value of it, then the getter function is invoked. So here, this would be the place where we actually define how the circumference for a rectangle is defined. And that's simply 2 times width plus 2 times height. And then whenever the circumference field is actually read in a println statement as a function argument or so, then this code will be invoked again, will be called again. We can also get rid of this getter here and just say, hey, the circumference is actually equal to this. That also works and would execute this code only once when the class is created, but not every single time the value of this field is read. In this case, this is actually smarter because the circumference will never change if we set the width and height values for a rectangle once. But if these values here could change across reading the value of this circumference across multiple reads, then it would make sense to make this a getter instead. And same thing is the case for the setter. So that also is also a thing which would be invoked whenever we assign a new value to a field. But that setter doesn't exist here for vals, since vals can change by definition. So we now only get an underline for area, which comes from shape, but we don't explicitly override it, which is a requirement. So we just need to prepend this override keyword, and then our class is happy, because we now fully conform to the rules of this shape interface. Let's also define this for a circle, since a circle is certainly also a shape. Oops, not that one, shape. Then we give this area an override. And then we also override the circumference here. Well, and for circles, that is calculated based on 2 times radius times pi. And it does complain here because it says property type is double, which is not a subtype of blah, blah, blah. So outcome of this calculation seems to be a double, but it expects a float here, since that is how we defined this. That happens because pi is defined as a double, since with pi we really care about accuracy and lots of decimal places. We could solve this, for example, by converting pi to a float, and then these errors are gone. But what we now really achieve based on this interface, that we make both these shapes implement this interface, that is how we call this, we are able to now pass instances of this interface. So we can have a function, some areas again. We pass in actually a variable number of arguments for shapes. And all these shapes are now of type shape and not specifically rectangle or circle anymore. And this will then give us a float that makes up the sum of these shapes. And here we could again use a typical function of the Kotlin standard library that takes in the Lambda function as an argument, which is called sum of. So this will now iterate over this list of shapes that we pass. And for every single shape, it will invoke this Lambda function. And we simply say current shape area. And this may again return a float, double here. Does that work? No. What actually will this sum of function return? We do need to make sure that we return this double here. Use this sum of overload of this that returns a double and then say double. But for some reason it does not really do this. Maybe we got an import here. No. So shapes.sum of. And the area, because the area actually returns a float, we need to say we convert this to a double. Because there is no sum of function that actually accepts float values here, so we need to convert this to a double. Now it's fine. So what this function does is it loops over all shapes, and for every single shape, it will sum up this specific value. So the area of that current shape, converted to a double. So if we now define two shapes here, our circle and our rectangle, and we then say we want to print the sum areas of both this rect1 and the circle, then that is perfectly fine. You can see that is the total area. And that now works because we defined the shapes to just be any type of class that conforms to this interface. Because that's all we need to know in order to know that any shape has an area. So we can obviously also sum up the areas of any shape. Something that is very similar to interfaces are so-called abstract classes. And those two are actually very often confused among programmers. So what we can also do is we can define this shape not as an interface, but as a so-called abstract class. So abstract class shape, and then we say we have an abstract val area, which is a float, and an abstract val for the circumference, which is also a float. If we then get rid of our shape interface and also call the constructor here of this shape abstract class, which does not have real constructor arguments, but every single class still has a constructor, and if it's empty, we just need to invoke it here via these opening closing parentheses, similar to a function without any arguments. If we do this down here, then everything else is the same. So if we run this again, then we will see we get the same area because we can still sum all kinds of shapes, and we now make this an abstract class. So what's the difference? An abstract class is in the end a real class blueprint again. So it's not only meant to define a contract like an interface does, to say, hey, the subclasses need to have this area and the circumference, because the moment we mark such a val or a function, by the way, as well, as abstract, that means, hey, we don't need to implement this here directly, but if a class says, I want to be a shape, then you need to implement this. And that again works via override. And abstract classes also have the behavior that we can't create instances of this abstract class directly. So we can't simply say that, hey, I just create a generic shape. I want to be a shape. This doesn't work because we can't create instances of abstract classes. We can only create instances of child classes of an abstract class. And this is what we call inheritance in object-oriented programming. So the moment we say a rectangle is actually a shape, then the rectangle inherits everything from the shape, or at least everything we define to be inheritable. In this case, it's really just the area and the circumference. But the main difference between an abstract class and an interface is that an abstract class can have normal functionality as well and also internal state. So wouldn't make any sense in this case, but just to show you the idea, we could have a counter variable here that starts at 0, and we then provide a function that actually increments this counter, and we say counter plus plus. That works because we've defined it that way. Every single subclass of shape will also get this behavior. It will also inherit that. So we could now go ahead and say rect1 dot increment. So even though we did not define this increment function directly in our rectangle, because it inherits from our shape class, which defines this behavior, not as abstract this time, because we have a concrete implementation here already. That means the rectangle and the circle will also have this function inherited from the parent shape. And they can also access this counter variable that comes from the parent. So if we now print this, print rectangle1 dot counter, then that will contain 1. So every single individual rectangle can now have its own counter value. If we have 2 rectangles, then the first rectangle has its own counter and the other rectangle has another counter. And they don't get in each other's way. So that is what I mean with internal state. In general, when you hear someone speak of state in the programming world, that just means to a value that can change over time. So in simple terms, just a var here. And this is something we can't do with interfaces. So that we have real values, like a counter that we can increment over time. We can provide default implementations of functions for an interface, but we cannot have variables in an interface that we already set in the interface directly and that we change directly in the interface. In most cases, you actually want to use an interface, but sometimes if you actually need a class to have such internal state and be inheritable, then an abstract class is what you should choose. You'll notice that if we remove the abstract keyword and also here, then we have to provide an implementation of these values, and then we also can't inherit from a class anymore. So normal classes or data classes are not inheritable. If we want a normal class to be inheritable without having this abstract behavior that we can't create an instance of this shape class itself, we would need to make the class an open class. So that is also a keyword that we can use here. And then we could say, okay, we actually have an open val area and an open val circumference, but we still get an error because we do need to provide a valid implementation here in the parent class already. Open just means, okay, we can inherit from that, but it also means it's not forbidden to create an instance of this shape itself. So it wouldn't make any sense in this case because we can't just have a shape. We always have to have a specific shape, a rectangle, a circle, some kind of polygon or so. But just that you have heard this once, that this open keyword exists, we would need to provide a default implementation here. Let's say 0f, for example, and 0f, then it wouldn't complain anymore. And we could still override this. So for all rectangles, this ruling is applied. For all circles, this one is applied. But nobody will actually complain if we don't override these fields. If we don't do that, then simply the implementation of the parent class will be used, which is, well, just returning 0 for all circumferences and areas. And with open classes, we could then also create a shape that is really just a shape. So invoke the shape constructor. And as I said, it wouldn't make sense because this would return 0 for every area, since there is no ruling behind how an area for a generic shape is just calculated. So here it really doesn't make sense to do that, but it's important that you've heard this open keyword at least once. But I want to quickly revert this to have an interface because that is really the kind of correct approach in this specific scenario with these shapes. Since our shape parent class does not have an internal state, we should make this an interface, have a val area of type float and a val circumference like this. And then an interface does not have a constructor, so we need to remove these parentheses again. And here we need to implement this again for the circle. So Command I, hit enter, and we say, okay, the area is actually radius times radius multiplied by pi to float we had. I could have just undone all this, but it's also quick to rewrite this like that. And we have the same code as we had before. And of course, what I didn't show you, we can have functions in an interface as well. So we have some kind of, I don't know, I can't think of a useful function here, but a hello world function. If we say this takes in a counter, I don't know, then we would actually need to override and implement this hello world function in each of these classes that conform to this interface. That of course also works, but let's get rid of that. If we have such interfaces and specific child classes that implement this interface, then we can also check which specific type a specific shape is actually. And that actually works really nicely with a when expression. So we could say when our circle is actually of type circle, then we say, yo, that's a circle. And if it is a rectangle, then we say that's a rect. We do get an error here because it says incompatible types, rectangle and circle. Because here where we create the circle, the code already knows this can only be a circle, obviously. But if the circle would actually be created as a shape, and we would get this in a function, for example, here, this would make more sense that we have the when expression down here, where we don't yet know one specific shape of the shapes list is. So we could say we want to print all these shapes as well, maybe in a separate function, print shapes, var arc, shapes like this. We then have our when expression here. When the current shape we're looping over, so for each shape in this shapes list, then for every single shape, we can now, if that shape is a circle, we print, yo, that's a circle, and otherwise that's a rectangle. So we can now say print shapes, rectangle 1 and circle 1, and if we run this, well, then it will say, yo, that's a rect for the first one, and yo, that's a circle for the second one. So that's also important to know that you can make these type checks here very, very easily with a when expression. That of course also works with if. So if you just need to check for a single type and not for all of them, then you can also say if shape is a circle, and then only do something here if the current shape you're iterating over is actually a circle. Something you will notice is if we actually don't print something here in the when branch, but rather return something like val output and then print the output, that's something we've done before, it actually complains because the when expression must be exhaustive. So we need to add an else branch here and actually also map these to the raw strings and not to print line statements. So if it's not a circle and it's not a rect, what kind of value should we then assign? So a when expression always must be exhaustive. So for all different possible scenarios, there must be one proper mapping if we want to just get a clear string out of that. For the print line statements here, it wasn't an issue because if something was not considered here, then the when expression simply wouldn't have executed any code at all, which is not an issue. But if we always want to print something and always want to get a clear string out of that, then we need to define a default behavior here, for example, null. However, there is another type of class that makes this a bit easier, and that's actually a sealed class or a sealed interface. Because if we now go to our shape interface and we make this a sealed interface, suddenly the else branch becomes unnecessary. And that makes sense because we know that a shape can only be a circle or a rectangle in the context of our project. So why do we need this else block, right? And well, that's exactly the behavior of a sealed interface. A sealed interface can only be implemented in your current project, or we call that in your current module. That is a bit more advanced what a module is, but in simple terms, it can only be extended. We can only define these shapes in our own code and not maybe by other people who use a packaged version of our code, for example. That's what a library would do. So just a predefined set of functionality that does not come from our own code base, but from an external one we want to still include in our own code base and use that functionality. Similar to how we use all these list transformation functions from the Kotlin standard library. That's functionality we did not add, but we still want to make use of. And the same way other people can just write code and provide this as a useful toolkit. But if you want to just provide a limited set of options for an interface or a class, then you can make this a sealed interface and it can only be extended in your code. But that has the advantage that your code base knows which possible options there are. So you don't need the else branch in a when expression, for example. A sealed class, as I said, can also be used. And that would be useful if you actually need this to have a constructor, which could make sense here. So we could also then pass the area and circumference, which wouldn't really make sense here because our shape does not need a constructor, since the area and circumference are provided by the child classes. There is a fixed calculation and there is no specific value we need to pass from the outside that every single shape requires. So if we have something like this and we don't require a constructor, then we should use a sealed interface. And if we do require a constructor for every single of these child classes, then a sealed class is more appropriate. Another class type that is very similar to sealed classes or sealed interfaces, but not the same, are so-called enum classes. So classes for a certain type of enumeration. That is why they are called enum classes. Because with enum classes, we can do something like this. We say we have an enum class, and I don't know, we call that country. And then in the class body, what we do is we can specify a list of countries. And here the naming convention for enum classes or the values of an enum class is actually snake case. So all uppercase and every word separated via an underscore. So for example, we have Germany, then separated with a comma, we might have France, the USA, something like that. So we can just enumerate a set of related options. And then we can also reference these in code. For example, I don't know, function greet me. We pass in a country and then we get back a greeting. And then we could say, okay, we return when country. And then in here, a little shortcut, by the way, is if we have such an exhaustive when condition and there is a limited set of possible options like here, 3 different countries that we want to support, or with a sealed interface, 2 different shapes. Then we can go inside of the when expression, hit Alt plus Enter, and say add remaining branches. And then the IDE will automatically give us these all possible options. So if a country is now Germany, then we could say something like Guten Tag. France, we could say bonjour. And in the US, we say hello. And then we could go up here and say, okay, instead of printing the shapes, we actually print a line and we say greet me from country.Germany. That is how this would work. We run this code and then we get Guten Tag. If we swap this out for the US, then we obviously get hello. So I think you get the idea. The class body of enum classes is quite different, of course, compared to what we did here with these data classes, normal classes, where we have actual functionality. That's rather uncommon for enum classes. It's possible we can give enum classes also an actual body and can write functions for them. But what's actually now the difference between enum classes and sealed classes? That's also a very common misconception or confusion among Kotlin developers. Because with sealed classes or sealed interfaces, we can also define a limited set of options. So for shapes, for example, we can say, hey, in the context of our project, we have rectangles and circles, and this list is exhaustive. That's all we have. And the same thing, we could go ahead and, of course, create an enum class for shapes. And then say, hey, we have a rectangle, a circle, I don't know, maybe a square. So when should you use which? What's important to understand about enum classes is that all options that we specify in here, so every single possible value of this enum class, is effectively a constant value. And a constant value means the value of that value is already known at compile time. So the moment we hit run, then our program must already know what specific value Germany represents. There is nothing dynamic about that anymore. However, if we think of our shapes again, like rectangles, then that is not really a constant. There is not just a single rectangle in our code that has a single fixed width and a single fixed height. No, there is actually a use case to have multiple different individual rectangles that all have their own dimensions. And these dimensions are not always known at compile time. However, for example, with countries, depending on how we use these, of course, that is pretty constant. And also if we add a constructor here, for example, to this country, we could say, okay, each country has a country code, which is a string. And then we could say, okay, that is DE. So now, since all these are constants, we need to call the constructors here inside the enum class already. Then we say France, and we say we have something for the US. Because now this country code is always the same for the specific country. We will never have a Germany instance that does not have this specific country code. So it's again something that is constant about this specific country. And if that is the case, you need to model something where you have a limited set of options, like in our case the countries, and all data that belongs to each country, which we specify in the constructor of this enum class, must also be constant. Then make sure to use an enum class and not a sealed class. So you always need to ask yourself, would there be a scenario where I could create 2 instances of Germany and that would make valid sense in my code? Well, and here in this example at least, it doesn't. There is only one Germany and therefore we only need one single constant value for Germany. Another cool perk that enum classes offer that sealed interfaces and sealed classes don't is that with the enum class, we also get some extra generated fields or functions. Specifically this entries function, we can actually loop over this. So we could say for every single country in our country.entries list. And we simply print this. So print country dot, for example, printing the country code. If we run this, then we get all the country codes. And this is now very useful because we can make certain parts of our code base dependent on all these entries in our country enum class. So the moment we actually extend this with another country, and we can, by the way, put this in separate lines here. So the moment we extend this with, for example, I don't know, Brazil, for example, and then we add Brazil's country code, then our when expression here isn't exhaustive anymore. Then we would need to add this here with Brazil, and I have honestly no idea how people greet each other in Brazil. So if you're from Brazil, let us know in the comments. I'll just use the AI auto-completion and we say Brazil. So if we run this again, then just by extending our enum class, we automatically change the behavior of this for loop, because the moment we add another country, this will automatically be included in this entries list. And this can be super useful in the real world. So For example, in Android development, we often have these drop-down menus where we have multiple options to select from. And very often, all these drop-down menu options that we could click on are modeled as an Enum class. And if we now want to extend this drop-down menu, all we need to do is we need to extend the Enum class, and we don't need to care about any other parts of our code where we maybe display this specific drop-down menu, because it just depends on the specific country entries or some other kind of Enum class entries list, and automatically extends the drop-down options in the UI of that Android app. All right, I think Enum classes should be clear. Then let's talk about one last type of class in Kotlin that is very worth talking about before we get to one more and actually the last topic for this course. And this type of class that we need to cover are so-called objects, or in other words, singletons. A singleton in software development is in the end just an instance of a class where there is only a single instance across the entire runtime of the program. So here in our case, this rectangle would technically be a singleton, since we only have one single rectangle, but it's not really a singleton because nothing keeps us back from creating multiple instances of that and passing these around. But sometimes there's real value of actually having just a single instance of a specific class in our code. And that's when we should create an object. So an object is really just the same as a class, just with the difference that it does not have a constructor. Because a constructor only makes sense if there is a unique combination of arguments that would make one single instance of that class unique. But if there can only be one single instance of that class, which is the case with objects in Kotlin, then there is no point in having a constructor, right? So for example, something we could do, which also wouldn't make too much practical sense in this case, but just that you get the idea, we could create an object that serves as a fixed size square or so. And this would then also implement our shape interface, because a fixed size square is also a shape. And then we can hit Command I to override these two fields here that we need in order to conform to this shape interface. And we can say, okay, the area is, for example, I don't know, 16. Let's say we have a side length of 4 and 4, and that actually must be float. And then the circumference must also be 16. So this way, by making this an object, we don't have a constructor. We can pass in a width value, which would be the only value needed for a square. But we say, hey, this specific instance of a square always has a fixed size. And then we can also reference this in our code. So we could say print line, and we reference our fixed size square. And we don't need to pass anything else, because just referencing fixed size square already refers to the only single instance that we have in code, which is exactly this one that we define here with these fixed dimensions. But we could still also reference its area, and we could perfectly pass this fixed size square in the list to our print shapes function. You can see the when expression actually now wants us to check for that as well. And then we can say that's a fixed size square. So that's definitely something we can do. If there are data classes, there are also data objects. Although the advantage of data objects over normal objects isn't that big anymore, because we can't copy them, since there is no way to actually create another instance of a data object. But this still comes with a bit nicer print line statement and has some more advanced benefits that would be too much to go into here. But under certain unlucky situations, it could happen that there are actually two instances of a normal object. And if they are then compared, then they would be compared based on reference, just like the normal classes. But with data classes, then this wouldn't happen. But that's something that can happen very rarely under certain circumstances. If you want to look into this, check reflection. But that's really beyond the bounds of this simple crash course. And I know, maybe this example is not the best one, since there is no real use case for such a fixed size square. We could simply create a rectangle and give it the same dimensions, so same width as same height. So same width and height. So I don't think there would be any type of shape where it would make sense to make that an object rather than a class, since in order to have a valid dynamic area, we would need to have some sort of other metric. So be it a radius, be it some kind of width or height. But in a lot of cases, it actually does make sense to have data objects, specifically if you need to inherit from a class or implement an interface like we do here, and the class that implements it simply does not need a constructor and also does not have any internal state that makes an instance of this class unique. In that case, you can make it an object, since you only need a single instance in order to make sense. Very often, such objects are also used to just bundle related functionality, so just as a container for functions. So we could do something like date util, and in here we could then of course write functions like format date we pass in some kind of date. So that would be a representation of a date in Kotlin, for example, this one here. And it then returns a formatted date string based on a specific pattern, for example. It's just commonly done to group such related utility functionality in an object so that we can directly reference the object and have all the related functionality included in our autocompletion. So we could then type dateutil.formatDate. So we don't need to remember the exact name of this function here, but rather just know, okay, in dateutil, all of my date-related utility functionality is contained. So I just need to write dateutil, and then I can easily find all those functions that you maybe don't want to remember. So that's another use case of objects or singletons in Kotlin. One last thing about classes before we get to the last topic are so-called visibility modifiers. So something we haven't talked about yet is if we have a class, for example, like a rectangle, and we specify a val or some kind of variable inside that class, then by default, it gets the visibility modifier public. What that means is that if a specific property or function is public inside of a class, then this can directly be accessed from the outside, so from other functions, for example. So the moment we have a rectangle here and we can write rect1.diagonal, that means this diagonal property must be public because otherwise we couldn't access it here at a different place that's not directly inside the class of the rectangle. However, sometimes you do just need certain variables or certain functions that are only needed inside of the scope of this class, but not outside. In these cases, what you can do is you can add the private visibility modifier. And the moment you say something is private, this diagonal can only be accessed here inside of this class body, but not outside anymore. So here we can say rect1, but diagonal does not appear anymore because we've now declared it as private. And in general, it's of course always a best practice to not make a specific variable or function more public than it needs to be. So if you really only need a field inside of the class, then make it private. So you only expose in a class what really needs to be exposed and what other classes, what other files, what other functions may need to access. There's also another visibility modifier which is called protected. This doesn't make sense here in this context. Protected should only be used if you actually have a parent class, so be it an open class, be it an abstract class. But if you declare a property in an abstract class, for example, so if we again have our abstract class shape, and we have an abstract, actually not an abstract val here, but for example, a protected val, let's just call it counter again, then a protected will mean this property is accessible and can be read inside of the shape class, but also in all its child classes, but not outside anymore. So the moment we create a shape, we could not access this counter. But if we have this in a parent class, like this abstract class, our child class inherits from that, then we could access the counter here somewhere in our child class. And lastly, there's also internal, which is also a visibility modifier in Kotlin. That is something you won't need as a beginner. It will make the field internal to the module you are currently in. Same thing as I mentioned before. If you're, for example, providing your code as a toolkit to other developers, as a module, as a library, then internal might be more used. But if you really just work on your own single project and you don't expose anything to other developers, to other modules, that is something you usually don't need. Let's remove this. And I think we can put a check to classes. Of course, there are lots of more little details about classes that you can learn about. For example, there are operator functions, so you can actually define your own operators and override these for a specific class so that you can define what it would mean if we say rect1 plus rect2, how this addition would work. That's behavior you could define with Kotlin for all kinds of operators that Kotlin offers. There are ways to define multiple constructors, but what I showed you here is really the most important foundation about classes with which you can directly start in the real Kotlin development world. The last topic that I want to talk about, and that is actually a little bit smaller topic than classes, that was already the biggest one, but the last topic is called generics. And we've actually already worked with generics here in this course without actually consciously noticing that. Because let's go back a little bit. Let's go back to when we applied our filter lambda. So we had some sort of, let's actually get rid of all that to not confuse you with this class stuff, like this. So we have a good old plain empty main function, and we have our favorite numbers array, for example. We have a favorite numbers array. That's an integer array of same numbers as before, like this. And we maybe have our hello world string. I don't know. We just define this here so I can showcase what I mean. We then actually made use of the filter function in order to say something like, okay, even numbers, that's something we had by saying favorite numbers that filter, and that's always the AI auto-completed code. But at the same time, we can say, okay, we actually only have letters. So letters only, that's the example we used, which is hello world or hello world string. And we filter it by checking if each character is actually a letter. And if you've actually watched carefully, you have maybe noticed something interesting. This filter function is called on an integer array here. And this filter function is called on a string here. And specifically also, if we go back a little bit, a string is just an array of characters. So this filter is called on an array of characters, and this filter is called on an array of integers. So both times we are actually iterating over an array, but the type of elements, that differs. And still we can call this filter function. So that is how we get to generics. Generics are in the end also a form of function parameters, so something that can differ depending on the function call, but the actual information that differs with generics is the type information with which we want to call a specific function. So we can define generic functions that work in a very generic way, like this filter function, to say, okay, in the end, if we want to filter something, we only care about the object that we call this on being iterable in some sense, having just a pool of elements. But we don't care about whether these elements are characters, integers, floating point numbers, rectangles, whatever. As long as we have a set of elements, we can apply a filter. And that's actually what we can see if we hover over filter here. Well, for arrays, it's actually a little bit different apparently. So you can see this filter function directly extends an integer array. So we can only call this an integer arrays. Let's see how this works with filter here. This is also defined as an extension function of string, but there must also be a filter function, for example, for list. So if we have our list of data here, for example, we say we have a list of 1, 2, 3, and we now want to filter that list. Then we will notice something interesting, because here it actually extends an iterable of type t, not of type integer. So we do have a list of integers. This type t is in the end the generic type parameter that defines, hey, as long as we have an iterable, and we don't care about the specific type of iterable, so whether it's a list of integers, a list of strings, a list of rectangles, and so on, as long as we have something we can iterate over, then we can also filter it, and we just give back a list with the same type that we called it on. So we don't need to provide an explicit extension function for a list of rectangle, then the same function again for a list of string, the same function for a list of integer. That's not very generic, not very flexible. Because what we can do instead is, we can say we have a function that extends the data type list. And here we could say we just want to extend a list of integers with our custom myFilter function. And we had this before. This is nothing new to you at this point. But if we do it like this, then we can only call this on lists of integers. But we can of course also filter lists of strings. So instead of passing in an integer here, we want to pass this type t. That is the generic type parameter. And if we want to make use of generics, then we need to also prepend this t here in angle brackets before this function. So this is just the name of the type parameter that we will use in the context of this function. We could also call this type or anything, but t is typically just a convention. If you have a single generic type parameter, then we call it t. That's very established, not only in Kotlin, but also in other programming languages. So we have a type parameter t that is dynamic and differs between different function calls of this myFilter implementation. The list that we extend must be of type t, but then we obviously don't just get integers here, because if we call this, if t here is a string, then this would also be a string, right? So instead of hard coding the integer here, we would need to include our t. So whatever kind of list we call this on, that's also the data type that we get in our Lambda. And that's also the data type that we get here in the return value. So we call this on a list of string, for example. Then in this single function call, t will be string. That means the predicate will also give us string elements because we iterate over every single string in that list. And for every single string in that list, we call this predicate. So if t is a string, then this will be a string for this particular function call. And as a result, the filtered list with a few strings being filtered out, that's again of type string. So I think this makes sense. If we quickly write the implementation here, then we could do this, for example, with a result list, which is a mutable list of, so a list where we can dynamically add more elements. Now we can't use this build string function anymore because we're not strictly dealing with a string, but with a list of data. So we just need to start off with an empty mutable list of type t again. That's the type of element we want to store in this list, and it's dynamic. And then we just iterate over this list that we called this function on. So for every single element in this, so this list here that we call this on, and here in the current in the current function execution, we don't know what this function might be called on, because one call might be called on a list of strings and another call might be called on a list of integers. But we can still work with this. So we can still say our predicate with our current element that now also takes in a type t. So element is of type t and our predicate takes an input of type t. So that is perfectly valid. If that returns true, that means we want to keep the element. That means we will simply add it to our result list. So .add element. And after we've done that, we've only added those elements for which the predicate function returned true, which we want to keep in our list. And then at the end, we can finally return our result list. And typically we also convert this to a read-only list by saying .toList, so we can't add more elements to it directly here at the call side. But if we now go ahead and we say we have a strings list, which is a list of some strings, hello world, we have another string, bye-bye, and one more, how's it going? And we have a list of integers. So integers is equal to a list of 1, 2, 3, 4, 5, for example. Then on the one hand, what we can do is we can say we have our filtered strings by saying strings list dot myFilter. You will see this can be called on a list of strings. And here in the scope of our Lambda, the behavior will be exactly the same. So we do get the current string, current string like this. And if we hover over this, we see this current string is of type string in this particular function call, in this particular Lambda, because we've called this on a list of strings. And then we can say, okay, we maybe filter this based on the current strings if it has a length of at least, let's say 8. So the strings that have at least 9 characters will be kept in the list and the rest will be filtered out. Or let's actually make it 10, because I think this fits better to the examples that I've chosen. On the other hand, we can have a filtered numbers list, which is equal to our integers, myFilter, that also works. And we say we include all numbers that are less than 3. And then we can simply print those two, so filtered strings and our filtered numbers. Run this, and you can see that is working pretty well. So the first time we filtered based on the string's length. The bye-bye string is not included anymore because that has a length smaller than 10. And here we include all numbers that have that are simply less than 3. And all that with a single function that is now generic and works for any type of lists. And the same way we can apply such generic arguments to a function, we can also apply them to classes. So very commonly what we, for example, do in Android development is that we define something like a sealed class called result. And this result class has a generic argument, which we again call t. But again, we can also call this differently. This is nothing that the IDE wants from us. It's just a convention that these are often called t. But if you feel like there is a better name, especially if we have multiple of these to indicate which stands for what. So we might have a generic type d and another type parameter that could be a different one of type e. Then this is a common way to actually implement a class that either holds a success result of something. For example, you made a call to some kind of backend server in your Android app, and that could of course succeed, so you get the valid data back from that server, or it fails with some kind of error code. If it succeeds, you maybe want to say, okay, I have a data class success, where we say, okay, this is the specific type of data that this now holds, because multiple different endpoints, multiple different routes you access from the server might return different types of data. So this might be dynamic. And then you could say, okay, here we have our actual data, which is now of type D for data. In that case, you could say, okay, that's actually a result. So our sealed interface declaration of type D. So now we need to provide both of these generic arguments here for the parent class. Well, and in the success case, we don't have any error type. So that would be the the type of error that happened for a specific failure. If it's successful, there is no error. So we could say we pass nothing. That is a special class in Kotlin that could be used in such a case. And then, well, we invoke the constructor. And I think I have the wrong import here for, yes, we need to remove this because there's also a result class that comes directly from Kotlin. And it had a naming conflict, but if we remove the import, then you can see there is no more error, but we would also then have maybe a failure class, which now only holds the error type because in the failure case, we don't have any successful data we got. So here we would get an error of type E, which is the result of nothing in this case for the data type. And we pass our error for the error type. And that could also be a sealed interface, by the way, since we don't have a constructor, so we can get rid of these constructor calls here. But that would be a popular use case for generics in a class, so that we now could have something like, for example, we have a function, make network call, and this now returns a result of something very specific, for example. So a result of string and, well, let's say a result of integer and an error of type string. Just for a very specific network call. Another network call might not return an integer as a validator, but maybe a rectangle, I don't know. So here we could then say we make a network call and then return result.success. And this now expects us to actually pass this data we maybe fetched from the network as an integer, because we say this specific HTTP endpoint needs to return an integer value. Or in a real use case, you would maybe fetch a list of data you that display in an Android app or so. And that would then be the piece of data. But if we now return a result.failure, then this refers to the error type, because we've specified that to be the type of error. So the second generic argument that we have here. So we need to pass in an instance of a string here, since that is what we specified. Hey, the specific result we return in this specific function for this specific network call has an error of type string. But an error could also be, for example, an instance of an enum class. So you have a set of errors that could happen for something. Imagine you are validating a password. Then there is just a limited set of things that could go wrong, like you're missing special characters, the password is too short. So you could bundle those related errors and pass this as an error type here. So at the place where you then use this function, for example, here you say something went wrong, then you will notice we actually get an error because it says it required a result of integer and string, but it got a result.failure of type string. So we say we want to return a result in this specific format, but we then return a result.failure, which is technically not the exact same data type. However, since result.failure is actually a subclass of this result class, this would still be valid, right? To pass a failure result to where we just expect a generic result, a general one. And that works, but we need to say, hey, these generic arguments are actually out. So we say we have this out keyword, which we apply before these generics. Then we don't have any more errors. But what we achieve with that is that we not only expect type arguments specifically only of this specific type D, so here, of result of type integers, but also we allow the subclasses to be passable here. So result.failure, for example, which is certainly a subclass of result. So it implements the sealed interface. So therefore it's valid. And if we now use this make network call function here somewhere, result is make network call, then this result, a result of integer and string in this specific call. But in another call, it might be a result of, I don't know, a rectangle and string, or of rectangle or some kind of error code, or a list of data could also be a specific successful data type. I know if you're completely new to the programming world, this is very complex, and that's completely normal. It also took me a while back then to understand generics, but they are super, super useful. Another example of a function where you need two generic type arguments is the map function. You've seen this before. So if we say we use map here and we actually check the function signature by hovering over it, then you can see this actually makes use of two generic arguments, t and r, where t is the type of class that we call this on, so an iterable of type t, for example, integer. And r is then the class or the type that we want to map each element to. So here, for example, if we do something like it.toString, so we just have a string representation of all integer numbers in here, then we can say mapped numbers, and then print this here. If we now run this, then here we don't see any difference, but these numbers are actually just strings in this case. Or something that maybe makes this a bit clearer is we map this to doubles. So then if we run this, every number is now not an integer anymore, but we've mapped every single one to its specific double representation. And that makes sense because if we again hover over this map function, this R type is the final type. So what we map these to, and these might of course be different. So we call this on an iterable, so a list here in our case, which is an iterable, of type T, of type integer in our specific case. And we then map this to whatever we have here in our Lambda expression. That is now type R, and how the R type is inferred. It sees, okay, here in this Lambda function, the developer is actually returning a double, because that's the return type of this toDouble function. So that means the R type must be of type double. So the resulting list is of type R, so in our case, of type double again, which is why we get a list of doubles here. But as I said, if you don't grasp these concepts like generics, also Lambda functions, I know the syntax of that is something you need to get used to. If you didn't grasp every single detail of every single type of class in Kotlin right away, really don't worry. That is completely normal. Learning programming takes a little bit. It's important that you've watched up to this part. Congratulations, by the way, it's quite a long video. But from this point on, what really matters is that you use this knowledge in some kind of practices. For example, in my older Kotlin Pro, Newbie to Pro playlist, it's called, I have homework assignments at the end of the videos. So if you need certain homework assignments, then check these videos. Just scroll to the end in case you are already familiar with this topic, or watch these again. And then do these homework assignments. Or maybe go to some kind of coding challenge website, like codewars.com, for example, where you just have to solve little programming problems with some algorithms. That's a perfect use case to actually practice such a programming language with. But once you really feel confident with these Kotlin language features, so everything we've covered in this course, then I would really recommend to get into something specific. So be it native Android development and building your first little app, be it backend development, for example, with Ktor or Spring Boot in Kotlin, which I will soon also make videos about on this channel. So if you've watched up this part, it's probably already online, so check my channel. Of course, subscribe if you like this. But Kotlin is really a great language. Use it, and I think it will also have a quite bright future on the market. In case you are actually into Android development or want to get into Android development, then really just check my channel. I think I have 1,000 videos right now. Just about native Android development. I have a very dedicated advanced premium courses for which I will include links down below. So check these out if you enjoy my approach of teaching, but most importantly, leave a subscribe if you like it. Thanks so much for watching up to this point. It was a long video, but I hope I see you back in the next video, and I wish you an amazing rest of your week. Bye bye.